Picture a warship that served for decades, armed, deployed on long voyages, drills, maybe even wars, and then one day it's no longer needed. What happens to a giant like that after its service ends? At first glance, you might think an old naval vessel just gets cut up for scrap, and that's it. But in reality, its disposal is one of the most complex and dangerous industrial operations out there, where military secrecy, environmental concerns, heavy metallurgy, toxic materials, logistics, and massive costs all collide. Because a warship isn't just tons of steel. Inside, you'll find fuel, oils, cables, electronics, hazardous materials, weapon components, specialized equipment, and in some cases, even a nuclear reactor. So decommissioning a ship after service isn't like tearing down a shed or scrapping a regular hull. It's a tightly planned industrial process where every step follows strict safety, control, and accountability protocols. Today, we're breaking down how military ships go from fleet retirement to recycled metal, and why this undertaking is so complicated and expensive. It all starts not with the cutter or shipyard, but with official fleet decommissioning. The vessel stops being an active combat unit and enters an entirely different status. But scrapping hasn't begun yet. First, the ship is prepped for transport and dismantling. Hull inspections, stability checks, towing plans, and assessments of internal compartments and external structures are completed. A key task? Preventing flooding, listing, or accidents before breakdown starts. The ship may be technically dead as a combat unit, but it's still a massive, complex structure that must reach a specialized facility safely. Only then does the transition begin from military asset to industrial recycling object. Right here, it becomes clear. Ship scrapping isn't a one-time event, but a lengthy project involving military personnel, engineers, contractors, environmental agencies, and metal recycling plants. Before they start cutting into the hull, the ship is stripped bare from the inside out. Equipment gets pulled, anything reusable is removed, and anything sensitive gets destroyed. Weapons, classified electronics, special communication systems, combat control elements all go through mandatory demilitarization. That doesn't just mean removal, they're deliberately deformed or destroyed according to strict protocols to prevent future use. Meanwhile, some equipment might get sent to warehouses and reused on other active ships if it still holds value for the fleet. This selective dismantling saves money, but it massively complicates the whole process, because the ship can't just be sent straight to the scrapyard. It has to be carefully inventoried and taken apart like one enormous collection of systems. Basically, before you can recycle the metal, you first have to separate it from an entire world of military technology that's been accumulating inside that ship for decades. Once the equipment's stripped out, one of the most critical phases begins: removing hazardous materials. Warships are packed with substances that would be serious environmental and safety threats in civilian life. We're talking residual fuel, oils, hydraulic fluids, bilge water, asbestos insulation, heavy metals, old paint, cable materials, and, on older vessels, compounds like PCBs. You can't just leave that inside and start cutting the hull with torches. First, all fluids get pumped out, because cutting could trigger fires, explosions, or contaminate surrounding water. Then, specialists in protective gear remove toxic materials while constantly monitoring air quality. On large vessels, these operations are done zone by zone, section by section, keeping the process under control. In other words, the ship first gets cleaned like a hazardous industrial site, and only then becomes a candidate for mechanical dismantling. At this stage, mistakes cost dearly. Now we're talking not just about metal, but about people's health and environmental risks. Once a ship's been stripped of its dangerous guts, the actual dismantling of the hull begins. But it's not just chaotic cutting. The hull gets carved up in stages to keep the structure stable and prevent multi-ton sections from collapsing uncontrollably. The process breaks down into tiers. First come the primary cuts. The hull and superstructure get divided into large blocks, sized based on crane capacity and yard layout. Then those blocks move to protected zones and get cut further into panels, beams, and smaller pieces. After that comes tertiary processing, sorting and prepping the steel for sale, melting down, or direct reuse. All of this demands precise sequencing because a ship is a massive hollow structure where shifting loads can trigger collapse. So scrapping is essentially controlled demolition, governed by engineering math. What matters isn't just the force of the cut, but understanding how a multi-thousand-ton hull will behave as the structure weakens. The whole economic point of this operation is recovering materials, steel above all. A warship is basically a giant stockpile of metal, and most of its mass can be recycled. The bulk is steel, hull plating, bulkheads, structural members, superstructure. Beyond that, there's non-ferrous metal, copper wiring, brass and bronze fittings, aluminum parts, cable runs, and other valuable components. Non-ferrous metals are pulled out with extra care because they fetch way more than ordinary scrap steel. Some plate and sections go straight back into manufacturing or get reworked at rolling mills. The rest goes to the smelter. From an industrial standpoint, it's a major source of secondary raw material, since recycling shipboard steel takes far less energy than making fresh steel from ore. So, scrapping ships isn't just about retiring the old fleet. It's a huge channel for putting metal back into the economy, even though the process itself stays extremely expensive and labor-intensive. Nuclear-powered vessels, mainly nuclear submarines and certain large warships, occupy a category entirely their own and can't be scrapped like conventional ships. First, spent nuclear fuel is removed from the reactor and placed in specially shielded containers and storage facilities. Then, the reactor compartment itself isn't cut open like ordinary scrap metal. It's cut out in one piece, sealed, and transported to long-term storage or controlled burial sites. This isn't just heavy industry anymore. It's where nuclear safety, government oversight, and extremely expensive specialized infrastructure all intersect. If the sub had missile compartments, their disposal may also fall under separate international restrictions tied to arms control treaties. In the end, a nuclear vessel after service becomes not just a disposal job, but a highly complex government project where metallurgy is only a small piece. Everything else is nuclear safety, transportation, storage, and oversight, stretching decades into the future. So why is this industry considered one of the toughest and most dangerous? Because it combines nearly every industrial hazard at once. There's fire and explosion risk from cutting into old fuel systems, collapse risk from multi-ton sections shifting unexpectedly, toxic exposure from asbestos, heavy metals, and decades-old chemicals, environmental contamination of soil, groundwater, and air without proper controls, plus serious legal complexity, international hazardous waste regulations, documentation requirements, site certification, material tracking, and safe transport logistics. That's why modern disposal programs need far more than just cutters with torches. They need full infrastructure, detailed hazardous substance inventories, sealed containment pads, drainage and filtration systems, continuous reporting, and strict government oversight. Even then, scrapping military ships often loses money or barely breaks even on scrap metal sales alone. Too much investment goes into prep work, safety protocols, careful dismantling, and regulatory compliance. When you look at the whole process from start to finish, one thing becomes clear. Scrapping warships after their service isn't the end. It's the ship's final industrial transformation. First, it's decommissioned from the fleet, then stripped of weapons and classified equipment, cleared of fuel, oils, and toxic materials, then the hull is cut down piece by piece, metal sorted and returned to industrial circulation. And if we're talking about nuclear vessels, you add decades of monitoring reactor compartments and radioactive materials. Essentially, scrapping a ship is civilization in reverse. Everything built as a symbol of strength and military power now safely broken down into raw materials, waste, hazardous fractions, and reusable components. And that's where the real weight of this industry lies. It doesn't deal with new products. It deals with massive machines from the past, turning them into resources for the future. That's why scrapping warships isn't just cutting steel. It's a complex industrial finale to an entire era of service for each combat vessel.
Each year, humanity produces over 400 million tons of plastic, of which 23 million tons end up in the oceans, forming gigantic rubbish islands the size of entire countries. Consider the Great Pacific Garbage Patch alone, which covers an area 3 times that of France. Just imagine, this isn't merely rubbish, but a threat that kills millions of marine creatures annually. And by the year 2060, the oceans will be drowning in 141 million tons of plastic. But would you believe that this blot doesn't actually exist in the form we imagine it? It's an invisible trap concealing a secret. How an ordinary teenager invented a method to clean the oceans without engines, using only the forces of nature? And if you watch to the end, you'll discover revolutionary robots sorting rubbish faster than lightning, and the Interceptor, which blocks plastic in rivers using solar power. A secret that will forever change your perception of the planet's future. The waste management sector is undergoing a technological revolution, thanks to the introduction of artificial intelligence and robotics. At modern waste processing facilities, robotic arms controlled by sophisticated algorithms sort refuse at remarkable speed and with exceptional precision. Computer vision systems identify different types of materials, enabling a significant increase in recycling rates. Along a wide conveyor belt moves a continuous, chaotic stream of what we've discarded. Plastic bottles, crushed cardboard boxes, aluminum cans. To the human eye, it's simply rubbish, whilst for workers it represents arduous and hazardous labor. And there, above this flow, rather like a relentless predator, it hovers, the sorting robot. This isn't a humanoid android from science fiction films, but rather a high-tech industrial manipulator resembling a giant steel arm. Yet all its magic lies within. Its eyes aren't merely cameras, but complex, multispectral sensors that perceive the world quite differently from us. They can distinguish materials by how they reflect light and analyze their chemical structure in fractions of a second. The heart and brain of the system is artificial intelligence. Before being deployed on the job, this AI underwent intensive training. It was shown millions of images of various types of waste until it learned to recognize them flawlessly. In this way, the robot learned to identify PET plastic, from which drinks bottles are made, denser plastic for canisters, paper, cardboard, various types of metals, and glass. And so the action begins. The conveyor belt races onwards. The camera scans the flow continuously. Artificial intelligence analyzes the image in real time. Target identified, aluminum can, it sends the signal. And a steel manipulator makes a lightning-fast, almost imperceptible lunge. A pneumatic suction cup or mechanical gripper gently but firmly seizes the can, and with a precise movement, drops it into the appropriate container. Before the can has even landed, the robot's eye has already spotted a water bottle, and the arm flies towards the new target once more. Speed? A human cannot compare with it. Some models are capable of making 100 manipulations per minute. That's more than 1 grab per second. Accuracy? The robot doesn't tire and doesn't get distracted. Its sorting efficiency reaches more than 95%, which significantly improves the quality of recyclables. This isn't simply a replacement for manual labor. It's a qualitative leap, which transforms the problem of rubbish into a genuine resource. The sorted materials, heaps of rigid plastic, cumbersome metal structures, wooden pallets, lie in separate mountains. They've already been sorted, but they're still far too large. It's here that the real heavyweight of the recycling industry enters the arena, a machine whose work is controlled, brutal force. This is the hammer mill. Outwardly, it resembles an enormous steel box, but its heart is a massive, heavy rotor, studded with rows of exceptionally robust, hardened steel teeth or hammers. Its task is simple, yet critically important: to shred. When material is fed into its vast maw via conveyor, be it an old car bumper or an entire pile of plastic drums, a spectacle of unstoppable power begins. As it rotates, the rotor's teeth seize hold of objects, dragging them inwards, and with a deafening roar and grinding, tears them to pieces. Rigid plastic cracks, metal bends and rips, wood transforms into splinters. This process is a demonstration of pure physical force. But what purpose does this destruction serve? It isn't senseless obliteration, but rather a crucial preparatory stage. Firstly, the shredded materials become uniform in size, which makes them far more convenient for transport and subsequent processing. Secondly, it's a process of liberation. The shredder breaks down complex objects into simpler components, facilitating the separation of different materials from one another. And most importantly, it creates ideal feedstock for further recycling. A heap of small plastic fragments melts far more readily in a granulator than intact bumpers. Vast accumulations of plastic in the world's oceans, such as the Great Pacific Garbage Patch, represent one of the most pressing environmental concerns. Incidentally, do you believe this patch doesn't exist? Nevertheless, through bold engineering solutions, hope emerges for cleansing our marine spaces. The problem is so enormous it appears insoluble. How does one remove something the size of several countries? Most simply threw up their hands, but not Dutch teenager Boy in Slat. In his mind was born a daring yet brilliantly simple idea, which grew into one of the most ambitious environmental projects of our time: the ocean cleanup. The project's principle is not to chase the plastic, but rather to make the ocean itself deliver the rubbish into the trap. For this purpose, giant U-shaped barriers were created. The most intriguing aspect is how this system moves. It has no engines. It drifts passively, caught by the same forces that carry the plastic: wind, waves, and ocean currents. But owing to its design, the system moves slightly faster than the plastic. This creates a small but constant difference in speed. The barrier, rather like a giant shepherd, slowly but inexorably gathers its plastic flock within its U-shaped arc. The path to success wasn't straightforward. Early prototypes fractured under the onslaught of ocean storms, but after a series of trials and errors, the system began working effectively. Now, from time to time, specialized vessels approach the laden barrier and offload the collected tons of plastic. This plastic, from old fishing nets to minute fragments, is brought ashore, where it's sorted and sent for recycling, closing the loop. Realizing that cleaning the ocean without stopping the flow of rubbish is rather like bailing water from a leaking boat, the ocean cleanup team asked themselves a logical question: couldn't one simply plug the leak? After all, research shows that the overwhelming majority of plastic enters the ocean through only a small number of the world's most polluted rivers. Thus was born the Interceptor, a technology designed to tackle the problem at its source. It resembles an elegant, futuristic catamaran, anchored mid-river. It is entirely autonomous and runs 100% on solar power, courtesy of the panels covering its upper portion. Its design has been thought through to the smallest detail, so as to be maximally effective whilst not interfering with shipping.
Picture this: 8% of all CO2 on the planet comes from one industry: steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, zero coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads, the first vehicle in history made from steel with a zero carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal and blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green.
The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math. Around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution. And it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen. Pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1,500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI.
What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks, the first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better. Because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel, manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 Green Steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's Voest-Alpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy, it's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter. An electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun.
You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel. The hydrogen revolution has begun, and it will change everything.
Every hour, somewhere in the world, a metal component weighing over 50 tons is manufactured, and a single microscopic error in its machining can trigger a multi-million-dollar catastrophe. Picture a crankshaft as long as a bus that must survive 1 billion cycles of explosive force, or a cylinder block where a deviation the thickness of a human hair means scrapping a multi-ton giant entirely. But here's the mystery. How do engineers achieve micron-level precision when machining parts heavier than a tank? What happens in that secret quality control room where a computer measures thousands of points and can shut down the entire process? And most importantly, stick around until the end, because I'm going to show you the final operation where one tiny slip turns months of work into scrap metal. This is manufacturing where every thousandth of an inch is a matter of engine life and death. Ready to look inside? The first thing that hits you at this facility? The sheer scale. Forget your average car engine. Take this cylinder block, for example. It can weigh dozens of tons. This isn't just a casting, it's a complex, multi-layered masterpiece of foundry art, requiring special grades of steel or cast iron that can withstand unbelievable loads, temperatures, and pressures. And here's the crankshaft. In big engines, this thing can be as long as a small bus and weigh just as much. This component is probably the most critical. It has to endure the explosive force of fuel combustion, converting it into rotational motion. The blanks often arrive as massive forgings where every pound of metal already has its own story. The process starts with incoming inspection. Specialists check the chemical composition, scan for internal defects using ultrasound and X-ray equipment. Because even the tiniest hidden flaw in a part this massive could lead to catastrophe during operation. It's like a health checkup for a steel giant. Only after a thorough inspection does the blank get clearance to enter the machine shop. Moving these blanks takes serious muscle. That's why the shop is equipped with powerful overhead cranes capable of lifting loads that outweigh most ordinary machine tools. Mounting the part onto the machining center is a precision operation requiring coordination and experience. This is the first step in turning metal into might. Now we move to the heart of the shop, the cylinder block machining zone. This is where multi-axis machining reigns supreme. Before you stands a gantry-type milling machining center. It looks more like a small house than a machine tool. Its spindles, fitted with ultra-hard cutting inserts, can remove up to several hundred pounds of metal per hour. The first operation is roughing. The goal: remove excess stock, eliminate surface casting defects, and give the part its basic geometry. The speed and sheer aggression of this cutting process? Absolutely mind-blowing. Those streams of hot chips tell you everything you need to know about the energy being dumped into this transformation. But the real magic happens later, during finishing operations. Remember when we talked about precision? For diesel engines, perfect cylinder geometry isn't just important, it's critical. That's where boring and honing come in. Boring creates the cylinder holes with micron-level accuracy. The slightest geometric error means uneven wear, compression loss, and ultimately engine failure. And honing, that's the final touch. A specialized tool with abrasive stones creates a micro-texture on the cylinder's inner surface, what we call crosshatch. This crosshatch is essential for holding oil and ensuring perfect lubrication of the piston rings. We're talking about polishing at nearly molecular level, guaranteeing engine life measured in decades. These machines operate under strict temperature control. Any temperature fluctuation can cause thermal deformation in a part weighing several tons, which means losing precision. That's why the shop floor maintains a constant microclimate, and the machining itself can run for days. Up next, meet our next hero, the crankshaft. This component works under the most demanding conditions. It needs not only colossal strength, but perfect balance. Manufacturing it, an engineering masterpiece. First up, preliminary journal machining. On specialized CNC turning milling machines, the connecting rod journals and main journals take shape. Given the weight and length of the shaft, unique support systems are used here to prevent sagging and vibration during machining. The critical stage? Grinding. The shaft journals must have minimal surface roughness because that's exactly where friction with the bearings occurs. The smoother the surface, the less friction, and the longer the engine lasts. Special cylindrical grinding machines with highly sensitive sensors handle this job. Now, for the critical part, heat treatment and surface hardening. After grinding, the crankshaft journals undergo induction hardening or nitriting. What does this do? It creates a super hard, wear-resistant layer on the journal surface while maintaining the core's toughness and strength. This is essential so the shaft can withstand billions of load cycles. Think of it as armor for the engine's most vital component. Final stage, balancing. Given the massive weight, even a tiny imbalance can destroy the engine. That's why every crankshaft goes through dynamic balancing. If the machine detects a deviation, counterweights are added, or material is removed from the flywheel sections until the shaft achieves perfect balance. It's like tuning a violin, except instead of music, we get harmony of rotation and power. How do you achieve that kind of precision when working with such giants? The answer lies in the tooling and quality control. The tool itself is a high-tech product. Every cutter, every mill is equipped with carbide inserts or even synthetic diamonds. They have to withstand enormous temperatures and cutting pressures. Special coatings extend the life of these tools while keeping machining quality consistently high. In a dedicated tool room, there's constant monitoring of their condition, resharpening, and replacement. But the most important thing is quality control. After every key operation, the part undergoes rigorous measurement. Coordinate measuring machines help us with this. These machines, equipped with high-precision probes and laser scanners, can measure up to 1,000 points on a part's surface with accuracy down to a few micrometers. They create a three-dimensional map of the part and compare it to the perfect computer model. If the error exceeds the tolerance, the process stops, and the part gets sent back for rework or, worst case, scrapped. No part leaves the shop floor until the computer gives the green light on its perfect accuracy. And then, when all the components, the block, crankshaft, cylinder heads, connecting rods, have passed strict inspection and achieved perfect precision, they're ready for the final stage: assembly. This is a different shop, where sterile cleanliness reigns. Assembling an engine like this is no less precise a process than machining. All parts are thoroughly washed, removing even microscopic traces of metal chips and dirt. Specialists use torque wrenches to tighten thousands of bolts to a precisely defined spec. A mistake in torquing the cylinder head, for example, can lead to a blown gasket and engine failure. Every stage of assembly is tracked and controlled by electronic systems. Not a single bolt gets tightened without computer confirmation. After assembly, the engine heads to the test stand. Here it's fired up and gradually brought to operating conditions. Sensors measure temperature, oil pressure, vibration, power output. Any deviation from the norm, and the engine goes back for rework. Only after successfully passing all tests does the engine receive its quality certificate. These giants get installed on ocean vessels, locomotives, mining dump trucks, power plants. One of these engines can run for decades, churning out thousands of horsepower. And behind every hour of its flawless operation stand months of work by engineers, machine operators, quality inspectors. Manufacturing these engines is the pinnacle of mechanical engineering, where metallurgy, precision mechanics, and computer technology converge. And just like that, starting from a multi-ton forging, through rough and finish machining, through honing with precision down to microns, through heat treatment and balancing, through sterile assembly and rigorous testing, an engine is born, capable of running billions of cycles without a single failure. This is the story of how humanity learned to create steel hearts for the most powerful machines on the planet. Every crankshaft, every cylinder block, it's a symphony of engineering thought where an error of 1 micron means failure, and success means decades of flawless operation. When you see a massive ship crossing the ocean, or a locomotive pulling thousands of tons of cargo, remember, at its heart beats an engine, every part of which has passed through the hands of master craftsmen and the scrutiny of computers. This isn't just metal, it's the embodiment of humanity's drive for perfection, where precision is measured in microns and reliability in decades of impeccable service. You're holding $100 in your hand, a green piece of paper with Franklin's face on it. Light, thin, looks ordinary, but it's not paper, and it's not ordinary. This bill was printed in a building guarded better than the Pentagon. Cameras everywhere, motion sensors, armed security. Getting in there is harder than getting into Fort Knox. The paper for it was made using a secret formula: 75% cotton. 5 people in the world know the formula. Printed 3 times. Each time with different inks. Each time with precision down to a micron. One wrong stroke, and the bill is counterfeit. Checked by machines, every millimeter scanned. Rejects burned immediately. Not even one bad bill gets out. Because if it makes it outside, someone could forge it. This piece of paper is protected better than a vault in a bank. Watch till the end, you'll learn how money is printed, and you'll never look at a dollar as just a simple piece of paper again. Texas. Cotton fields stretching to the horizon. Heat pushing 100 degrees. White cotton bolls bursting on the bushes. Combines harvesting the crop. But not all cotton makes the cut for money. Only the longest fibers. White, strong, hand-selected, shipped to the factory, Massachusetts, town of Dalton, Crane Currency Facility. They've been making paper for dollars since 1779. Nobody else in the world has the rights. The grounds are guarded around the clock. Airport-level security screening. Cameras in every corner. Cotton gets mixed with linen. Boiled in massive vats. Water added. Creates a white pulp. Rolled into thin sheets. During the rolling, red and blue fibers get woven in. Randomly. Chaotically. Impossible to replicate the pattern. First line of defense. Then a security strip gets embedded. Thin metallic thread. Glows under ultraviolet light. Water pressed out. Dried. Cut into large sheets. Every sheet inspected against the light. Checking for defects. One air bubble. Sheet gets rejected. Finished paper gets packaged. Transported under convoy. Armed guards. Armored truck. Because if someone steals this paper, they can print real money. Washington, D.C. A building with no signs. Gray, nondescript. Inside, they print money. Bureau of Engraving and Printing. Security level like a military base. Metal detectors, retinal scanners, fingerprints. Even employees can't enter without triple verification. Cell phones banned. Cameras banned. Any recording devices confiscated. Inside, printing presses the size of a bus. Each one costs $10 million. Running around the clock. Sound like a jet taking off. Paper loaded in stacks. 32 sheets per stack. Each sheet will print 32 bills. First pass, background printing. Green patterns, fine lines. Hand-drawn by engravers for months. One mistake, start over. Lines so fine they're invisible to the naked eye. That's the second anti-counterfeiting measure. Special ink. Formula classified. Made at a different facility. Under the same level of control. Sheets pass through the printing cylinder. Come out green. Wet. Dried under infrared lamps. Every sheet inspected. Sensors scan color, density, line alignment. Precision. 1/100th of a millimeter. Thinner than a human hair. Second pass. Intaglio printing. The most important one. Franklin's portrait, the numbers, the text, all of it printed under massive pressure. 3 tons per square centimeter. The ink gets pressed into the paper. Run your finger across it, you feel the texture. That's the main security feature. Impossible to fake. Regular printers can't do this, even professional ones. You need a special machine. There are 10 of them in the world, and they're all here. The printing cylinder is covered in microscopic grooves. The design is laser engraved. Precision, 5 microns. That's 10 times thinner than a human hair. The cylinders get replaced every year. The old ones are destroyed, melted down, turned into scrap metal. So nobody can recover the design. Sheets pass through the machine. Come out with Franklin's portrait. Sharp numbers, raised lettering. Another inspection. Machines scan every detail. Compare it to the standard. If even 1 pixel is off, the sheet gets rejected. Rejects are set aside separately. Shredded at the end of the day. Burned. The ash dissolved in acid. Even the ash from dollars can't just be thrown away. Third pass, serial numbers. Every bill gets a unique code, 11 digits and letters. This combination doesn't exist anywhere else in the world. Printed in green ink, right side and left side. The numbers must match perfectly. The machine checks. If left and right don't match, rejected. Right then, they print the Treasury seal, green circle, and the Federal Reserve Bank seal, black. The letter shows which bank issued the bill. All of this happens in 3 seconds. The sheet runs through the machine, comes out with numbers and seals. Final inspection, the toughest one. Machines scan the bills under ultraviolet light, under infrared light, under magnification. They check 15 parameters: color, texture, security strip, watermark, line alignment, ink density, size, centering, numbers. Any deviation, rejected. Rejection rate, 3%. Out of every 1,000 bills, 30 get destroyed. Good sheets go to cutting. The rest, into the shredder. Cuts into individual bills. Precision, 1. Cuts into individual bills. Precision, 1/10 of a millimeter. If even one bill is cut crooked, the entire sheet is scrapped. Bills drop into a tray. A robot picks them up, counts them. 100 bills per stack. Wraps them in paper. 100 stacks per block. $10,000 in a single block. Blocks get wrapped in film, sealed, stamped with the date. Serial number, quantity, loaded into safe containers. Metal ones. Locked with 3 separate locks. 3 different people hold the keys. One person can't open it. Containers get loaded into an armored truck. Armed guards. 2 escort vehicles. Driven to the Federal Reserve Bank. There they're unloaded into the vault. Underground. Walls 3 feet thick. Steel reinforced concrete. The bills sit and wait until some bank requests them. Then they're pulled out. Counted, packaged, shipped off. Your local bank orders fresh bills. The request goes to the Federal Reserve. From there, they ship a container. Again, under guard. Brink's armored truck. 2 armed guards. GPS tracker, dispatch communication. Any route deviation triggers an alarm. They arrive at the bank, unload into the vault, check the seals. Open the container, count everything. By hand and by machine. The amount must match to the cent. Some bills go into ATMs. An operator loads the cassettes, $4,000 in one cassette. Inserts it into the ATM. Closes it up, a TM's ready. You walk up, insert your card, enter your PIN, request $100. Inside, rollers activate. Grab one bill, sensors check it. If the bill's wrinkled or torn, the ATM won't dispense it. Takes the next one, feeds it through the slot. You grab it, fold it into your wallet, and walk away. Never thinking about the journey that piece of paper took. From a cotton field in Texas to your wallet. Secret paper, triple printing, 15 inspections, armed guards at every stage. Now you know. This bill isn't just paper. It's the most protected document in the world. It was printed by people who passed security clearances, working on machines worth $10 million, under cameras and sensors. Any mistake, and the bill is destroyed, burned, dissolved in acid. Because even a defective bill in the wrong hands is a threat. Someone could study it, understand the technology, try to counterfeit it. That's why the security is so tight. You'll never look at a $100 bill like ordinary paper again, because now you know it has 300 years of technology encrypted in it. Red fibers in the paper are randomly placed. The security strip glows under ultraviolet light. Franklin's portrait is pressed under 3 tons of pressure. Microlines thinner than a hair. Serial numbers unique. This bill is impossible to counterfeit, even if you really try, because it wasn't made to be beautiful. It was made to protect money from counterfeiters, and it works.
Every year, more than 50,000 tons of uranium are mined across the globe. But to extract just a few grams of its energy, mountains of rock must be moved. It's a journey that begins in a desert where the temperature hits 38 degrees Celsius and ends inside a reactor that powers New York City. It involves centrifuges that spin faster than a jet turbine and chemicals that can dissolve metal in seconds. But the most interesting part is something that even the safety manuals don't mention. Watch until the end and you will learn a secret that will change how you think about nuclear power forever. It all begins in the dust, literally. Uranium ore is mined in hot, arid regions: Arizona, Wyoming, Texas, New Mexico. Here, the sun is relentless, reaching 38 degrees Celsius in the shade, if you can find any. There are two main extraction methods: open pit mining, where the topsoil is stripped away, and underground mining, with explosives and hoists. There is also a third, more subtle technique: in situ leaching. Pipes are drilled deep into the earth. Special solutions are pumped down to dissolve the uranium directly from the rock, and the resulting liquid is then pumped back to the surface. The ore itself, a grayish-brown rock, looks unremarkable, but within it, the crucial isotope uranium-235 makes up just 0.7%. The rest is a vast, almost useless mass that is inert in a reactor. And to squeeze the required drop of energy from it, hundreds of tons must be processed. After mining, the ore is crushed, milled into a fine powder, and thrown into a chemical bath of acid or alkaline solutions. This is followed by filtration, precipitation, and drying at 260 degrees. The final product is yellowcake, a bright yellow uranium concentrate. Officially, it's known as uranium ore concentrate, but everyone at the plant just calls it yellowcake. It looks striking, a mustard-colored loose powder like a spice for a barbecue. But this is a substance you must not touch and must never inhale. It emits alpha radiation, has a long half-life, and its dust is dangerously toxic. The yellowcake is sealed in double-walled drums, loaded onto escorted trailers, and plastered with radiation warning signs for the journey to the enrichment facility. This is the start of the path that turns a poisonous dust into the clean white light from a lamp over your kitchen table, or the electricity that powers the tube deep beneath London. Right, the yellowcake has arrived. It's radioactive, dry, and sealed in its drum. The next step? Turn it into a gas. And not just any gas. This is uranium hexafluoride. The uranium concentrate is first dissolved in acid, purified, and converted into uranium dioxide. And here, the alchemy begins. The uranium dioxide is treated with fluorine gas in special reactors at 540 degrees. The reaction creates a volatile, transparent gas that boils at just 56 degrees. A little heat, and it turns from solid crystals into a vapor. But it's not that simple. This gas is extraordinarily toxic. It corrodes most metals, destroys human tissue, and on contact with humid air, it instantly transforms into hydrofluoric acid and uranyl fluoride, a lethal cocktail. That is why this entire process is conducted inside sealed, automated reactors. The substance is stored as solid, whitish crystals, formed by cooling it to room temperature. These crystals are kept in steel cylinders, each engraved with a serial number and a radioactive symbol. A single cylinder weighs almost 14 tons. You think your washing machine spins fast? You haven't seen a nuclear centrifuge. They can reach 70,000 revolutions per minute, more than 10 times faster than a jet engine turbine. And all for one purpose: to separate uranium isotopes. Uranium hexafluoride, that toxic gas we just created, is fed into a tall, narrow cylindrical chamber, which is then spun at an insane speed. Centrifugal force does the work. The heavier uranium-238 atoms are flung towards the outer wall, while the lighter, crucial uranium-235 atoms remain closer to the center. But one centrifuge isn't enough. They are connected in cascades of hundreds, sometimes thousands. Each one slightly enriches the gas and passes it to the next. This process is repeated, cycle after cycle, until the concentration of uranium-235 reaches at least 3 to 5%. This is the standard grade for reactor fuel. Okay, the gas is enriched, but you can't feed a reactor with a gas. So now it is converted back into a solid, this time a ceramic form. After a series of chemical reactions, the gas becomes uranium dioxide powder, a dark gray solid. This powder is pressed under 20 tons of pressure into small cylindrical pellets, just 8 millimeters in diameter. They look almost harmless. Next, the pellets are centered in a furnace at nearly 1,650 degrees, making them as hard as porcelain. They are then polished and ground to precise dimensions. The finished pellets are loaded into long metal tubes known as fuel rods, typically made of a zirconium alloy because it resists corrosion and can withstand intense radiation. Each rod holds over 300 pellets. The rods are hermetically sealed and then bundled together into modules called fuel assemblies. They look like a square frame holding a grid of several dozen rods. A single assembly can weigh over 680 kilograms and will operate inside a reactor for up to 6 years. The finished fuel is packed into armored containers for transport. The journey is made under guard, on a special route with a security escort and GPS tracking. Left over from all of this is the depleted uranium hexafluoride, known as tails. It's a mix of isotopes with a small amount of U-235 remaining, but not enough to be useful. These tails are stored in steel cylinders at designated secure sites. When a fuel assembly has served its 4 to 6 years in the heart of the reactor, it is no longer a shining star. It is removed by a robotic system and moved into a deep pool of water, over 6 meters deep. The water cools the assembly and shields the intense radiation because the fuel is still incredibly hot. It rests there for several years. After that, it has 2 possible futures: long-term dry storage in concrete and steel casks, or reprocessing. This usually happens in other countries, as the US and UK primarily store their waste rather than reprocess it. In a dry storage facility, the assemblies stand for decades, cooled by natural air convection, as if in a nuclear monastery. This isn't the end, but a new phase of life. A slow, controlled existence, but one deeply connected to the future of energy. Because even after its time in a reactor, this fuel remains a source of heat, a lesson in engineering, and a reason for profound respect.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears. Yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory. This is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine. 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between two rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees. So the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms, internal stresses build up. Keep rolling without annealing? The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out, shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity. 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible. Imagine if construction could be not just strong, but ultra lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually, and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal. Every rock you hold in your hands could be hiding miles of wire. Sounds insane, but it's true. Copper ore, this gray-green boulder, holds millions of tons of metal that powers every city on the planet. Every wire in your home, every cable underground, every power line stretching across continents. It all started with a chunk of dull rock that got blasted, crushed, and melted at 2,200 degrees. Humanity extracts 25 million tons of copper every year. That's the weight of 4,000 Eiffel Towers. Each ton requires blasting 100 tons of rock, drilling hundreds of feet deep into the earth, processing mountains of stone, and all for a metal that makes up less than 1% of the ore's mass. How do you extract red metal from gray rock? Metal that conducts electricity better than anything else on Earth? How do pits nearly a mile deep give birth to wires that light up megacities? Stick around till the end. You'll see how rock becomes the energy of civilization. Chuquicamata, northern Chile. The Atacama Desert, the driest place on Earth. Home to the planet's largest open-pit copper mine. Depth, 3,300 feet. Width, 2.5 miles. Length, 3 miles. A wound in the Earth's crust, visible from space. Excavators the size of a 3-story building gnaw at rock around the clock. Each bucket, 700 cubic feet. In 1 hour, a single excavator tears out 1,000 tons of ore. Bel AZ dump trucks with wheels 13 feet high haul 300 tons per trip. The road out of the pit, a serpentine stretch 12 miles long. Trucks spiral upward for an hour just to reach the surface. Chile produces 6 million tons of copper a year. That's 28% of the global market. Peru delivers 2.5 million tons. China mines 1.5 million but consumes 14 million. The rest it buys. The US produces 1,200,000 tons. Russia, 700,000. Copper is a strategic resource. Without it, no power grids, no communications, no electronics. Countries fight over deposits more quietly than they do over oil, but no less fiercely. Mining starts with explosions. 100-foot-tall drill rigs bore 12-inch diameter holes 65 feet deep. The well pattern is calculated to the inch. Distance between holes, 16 feet. Each one gets packed with ammonium nitrate mixed with diesel fuel. ANFO, the cheapest explosive there is. One charge, 650 pounds. A single bench takes 400 tons of explosives. Detonation controlled by electronic timers. Each hole blows with a 10-millisecond delay. That creates a destruction wave that fractures the rock without throwing it far. The blast lasts 3 seconds. Sound like an earthquake carries 20 miles. The ground heaves. A 1,000-foot column of dust rises from the pit. When the dust settles, you're looking at 2 million tons of fractured rock. Excavators move in. 24 hours to haul it all out before the next blast. The conveyor never stops. Blast, haul, drill new holes. Blast again. The pit grows 65 feet deeper every year. "6,000 years ago, on the island of Cyprus, people found a strange stone. Green, heavy, with a metallic sheen on the break. When they threw it into the fire, the stone melted and a red liquid flowed out. As it cooled, it turned into metal, soft, flexible, shiny. The ancients called it cuprum after the island of Cyprus. They made knives, axes, jewelry from copper, but the major discovery happened in 1831. Michael Faraday created the first electric generator. Turns out copper conducts electricity better than any affordable metal. 6 times better than iron. 1.5 times better than aluminum. Only silver beats it, but that's way too expensive. Copper became the perfect conductor. In 1879, Thomas Edison built the first power station on Pearl Street in New York. Copper wires stretched through the streets. Cities began to glow at night. The era of electrification had begun. Demand for copper exploded. What was once used for coins and statues became the backbone of energy. Quarries expanded. Mines went miles deep. Humanity started devouring copper by the ton. The 20th century transformed copper into civilization's circulatory system. Every house requires 440 pounds of copper. Wiring, pipes, radiators. One car, 50 pounds of copper in the alternator, starter, wiring. One wind turbine, 9,000 pounds of copper in the generator windings. A Tesla factory for battery production, 22 million pounds of copper annually. A power transmission line across Siberia, 660 million pounds of copper and thousands of miles of wire. By the start of the 21st century, humanity was mining 33 billion pounds a year. By 2020, 55 billion, a 60% increase in 20 years. The reason? Electrification of developing countries. India's building new cities. China's laying high-speed rail. Africa's installing solar panels. Copper's needed everywhere. The problem is, rich ores are running out. Ore used to contain 5% copper. Now, 0.5%. To extract 1 ton of metal, you need to process 200 tons of rock. Pits are getting deeper, process is more complex, cost higher, but demand's growing faster. Ore from the pit heads to the processing plant. This is where chemistry and physics kick in. First step, crushing. Jaw crushers grind refrigerator-sized rocks down to 4-inch chunks. Cone crushers pulverize them to gravel. Ball mills turn gravel into sand. The mill's diameter, 26 feet, length, 40. Inside, steel balls weighing 110 pounds each spin around. They pound the ore, grinding it to powder. After 8 hours of rotation, the ore becomes dust. This dust gets mixed with water, creating slurry. It flows through flotation machines. These are giant tanks with air pumped in from below. Air bubbles get coated with flotation reagents, chemicals that stick to copper particles. Copper floats to the surface in foam. Waste rock settles to the bottom. The process runs through 10 stages. Each stage increases copper concentration. At the input, 0.5%. At the output, 25%. That's concentrate. From 100 tons of ore, you get 2 tons of concentrate. The remaining 98 tons? Waste that gets stored in tailings ponds the size of a lake. The concentrate heads to a copper smelter. Here it's turned into pure metal. First stage, roasting. The concentrate is heated to 1300 degrees Fahrenheit in the presence of oxygen. Sulfur burns off as sulfur dioxide gas. What's left is sinter, a mix of copper and iron oxides. The sinter gets loaded into a reverberatory furnace. Temperature, 2200 degrees. Silica flux is added. Iron bonds with the silica and floats up as slag. Copper settles at the bottom as matte, an alloy that's 50% copper. The matte is poured into a converter. Pure oxygen is blasted in under pressure. Remaining iron and sulfur burn away. Temperature climbs to 2370 from the exothermic reaction. After 6 hours of blowing, what's left in the converter is blister copper. 98% pure. But that's not enough for wires. You need electrolysis. Blister copper is cast into anodes 2 inches thick. They're submerged in tanks filled with copper sulfate solution. A current of 2 volts runs through. Copper dissolves off the anodes and deposits onto cathodes. After 3 weeks, the cathodes are coated with a layer of pure copper 4 inches thick. Purity, 99.99%. This is market-grade copper, ready to become wire. And just like that, after a journey from an explosion in a half-mile deep quarry through crushing, flotation, smelting at temperatures above 1800 degrees Fahrenheit, and electrolysis, gray rock transforms into red metal that carries electricity to every home on the planet. Without copper, there'd be no light in cities. No internet. Every data center runs on copper bus bars. No electric cars. A single Tesla contains 175 pounds of copper. No renewable energy. Solar and wind farms need 3 times more copper than coal plants. Every year, humanity lays down 6 million miles of copper wire. That's the distance from Earth to the Sun and back 7 times. 25 million tons of metal connecting continents into a single electrical grid. Copper is civilization's nervous system. Electrical impulses race through copper veins like thoughts through neurons. Factories operate, hospitals save lives, homes glow in the night. All thanks to metal that was once just green rock in the ground. Every time you flip a light switch, remember, between your finger and that bulb, miles of copper wire born from an explosion in a desert quarry on the other side of the world. It's the magic of turning stone into energy, and this magic won't stop as long as cities shine. $3 billion. Weight, 7,800 tons. Length, 377 feet. This isn't an aircraft carrier, it's not a spaceship. This is a single Virginia-class nuclear submarine. A machine that takes 7 years to build and can stay underwater for months without surfacing once. Inside, a nuclear reactor more powerful than what lights up a small city. Outside, a hull made from ultra-high-strength steel, capable of withstanding pressure at depths of 1,600 feet. That's deeper than the Empire State Building is tall. Every single part of this monster gets checked hundreds of times. One mistake, and $3 billion becomes a metal coffin on the ocean floor. How do you even build something this complex? How do you weld a hull that won't leak at depths where pressure would crush a tank? How do you fit a nuclear reactor inside so that 130 crew members can live next to it for years? Stick around. You're about to see how the deadliest weapon in the ocean is born. The Electric Boat Shipyard in Connecticut. 420 acres, 19,000 people work here. This isn't just a factory, it's a city where underwater fortresses are built. In front of you, a massive workshop nearly 1,000 feet long. Overhead, cranes crawl along the ceiling, each capable of lifting 200 tons. On the floor lie giant steel cylinders. These are sections of the future submarine. Each one weighs as much as 10 buses. There will be 9 of them. Right now, they're lying separate, but in a few months, welders will join them into a single body longer than a football field. Nearby stand other sections, already finished. Inside them, you can see pipes, cables, bulkheads. It's like a construction set, only every piece weighs tons. In another building, they're assembling the reactor compartment. Nobody gets in without secret-level clearance. Cameras, guards, radiation sensors. This is where they install the submarine's heart, the nuclear reactor. One wrong move, and the entire project's at risk. The process runs around the clock. 3 shifts of 8 hours. The boat can't wait. Construction begins with the hull, HU 80 grade steel. Sheet thickness, 1 to 2 inches. That's enough to withstand pressures of 730 pounds per square inch at depths of 1,640 feet. They bend the sheets on giant presses. Force, 2,000 tons. The metal groans but takes the required shape. Cylindrical sections are welded by hand. This is work for virtuosos. Every seam is X-rayed, the slightest microcrack, and the section is rejected. Welders work in protective suits. Welding temperature, 2,900 degrees Fahrenheit. A single seam can take 8 hours of continuous work. Inside the sections, they install systems. Coolant lines for the reactor. Electronics cables. Their total length exceeds 93 miles on a single boat. The ventilation system. The crew will breathe recycled air for months. Bulkheads divide the hull into compartments. If one floods, the others must hold. Every element is pressure tested. They fill it with water and watch. Does it hold or not? Defects are unacceptable. A mistake on the surface, an inconvenience. A mistake at depth, death. (1954), the world's first nuclear-powered submarine rolls off the ways, USS Nautilus. A revolution in naval warfare. Before this, subs were really diving ships. They cruised on the surface using diesels, then slipped underwater briefly, running on batteries. Nautilus changed everything. The nuclear reactor generated power without air. The boat could stay submerged for months. In 1958, Nautilus passed beneath the ice of the North Pole. Impossible before. A diesel sub would have suffocated within a day. But Nautilus cruised at a depth of 300 feet, and its reactor ran like clockwork. The Cold War demanded more boats like this. The Skipjack class appeared, then Permit, then the legendary Los Angeles. Each generation got quieter, deeper, deadlier. The Soviets built their own: November, Victor, Akula. The race was on. Who's faster? Who's quieter? Who goes deeper? The oceans became a battlefield for invisible giants. The Americans led in stealth technology. Their boats could hide so well that enemy sonars heard nothing but ocean noise. The 90s, the Soviet Union collapsed, but the submarine fleet remained a priority. In 2004, the US launched a new program, the Virginia class. This isn't just an improved version of old boats. It's a completely new philosophy, a multi-mission machine for 21st century warfare. The Virginia can do it all: hunt enemy subs, launch cruise missiles at land targets, deploy special forces, conduct recon off hostile shores, lay mines. The cost of a single boat climbed to $3 billion. But the technology is impressive. The hull is covered in special tiles that absorb sound. The boat runs quieter than rain falling on the ocean surface. The propeller's been replaced with a pump jet propulsor, even less noise. Inside, digital control systems. It used to take a crew of 140, now 130. Automation took over part of the work. Next-gen sonar hears targets 100 kilometers out. Torpedoes with artificial intelligence hunt the enemy on their own. This isn't just a boat. It's a floating fortress with a supercomputer brain. The heart of the boat is the reactor compartment. Here sits an S9G reactor. Output? 210 megawatts of thermal energy, enough to power a small city of 100,000 people. But here, all that power drives the turbines. The reactor heats water to 570 degrees Fahrenheit under 2,200 pounds per square inch of pressure. The water doesn't boil, the pressure keeps it in check. This superheated water flows into a heat exchanger where it converts the secondary loop into steam. Steam spins the turbines. Turbines turn the shaft. The shaft drives the pump jet. The boat moves. Submerged speed? 25 knots. That's 28.5 miles per hour. Doesn't sound fast, but for a submarine, that's serious. And here's the kicker. fuel lasts 33 years. The reactor never needs refueling for the entire service life of the boat. Inside the core, uranium-235. Enrichment level, 97%. That's nearly weapons-grade uranium. Radiation shielding, a 3-foot-thick layer of lead and boron. The crew lives 100 feet from the reactor and gets less radiation exposure than airline passengers at 33,000 feet. Safety tech proven over decades. The weapons can destroy an enemy fleet or wipe a city off the map. 12 vertical launch tubes. Each one can carry a Tomahawk cruise missile. Range, 1,500 miles. The boat surfaces to launch depth, 160 feet. The tube cover opens. The missile shoots out using a gas generator. At the surface, the main engine kicks in, and the missile flies to its target. Accuracy, 16 feet. You can hit a specific window in a building thousands of miles away. 4 torpedo tubes, 21-inch caliber. Mark 48 torpedoes, with wire guidance and active target seeking. Torpedo speed, 39 miles per hour underwater. It can chase its target, maneuver, bypass decoys. One hit, and a ship displacing 10,000 tons goes to the bottom. Electronic warfare systems jam enemy sonar. Decoys create false targets. The boat knows how to fight and how to run. Its job, stay invisible until the last moment. And when the enemy realizes they're under attack, it's already too late. And just like that, after 7 years of work by 20,000 people, a machine emerges that embodies the pinnacle of human technology. Every inch of this boat, the result of decades of engineering thought. Every system tested through thousands of hours of trials. This isn't just a chunk of metal with a reactor. It's a symbiosis of physics, chemistry, metallurgy, electronics, and human craftsmanship. Inside this steel tube, 130 people will spend months away from the sun in the eternal silence of the depths. They'll eat, sleep, work in an enclosed space the size of a small house. Above their heads, miles of ocean. Beneath their feet, endless darkness. But they know they're protected by the best engineering in the world. A nuclear submarine is more than a weapon. It's proof of what the human mind can achieve when technology meets will. $3 billion, 7 years of labor, thousands of tons of steel and knowledge, all for one purpose. So that deep beneath the waves where light and sound don't penetrate, an invisible force swims, capable of changing the course of history with the push of a button. The ocean no longer belongs only to nature. Humanity has learned to master the abyss. Every year, dozens of nuclear submarines get retired around the world. Steel giants weighing over 10,000 tons. Inside each one sits a reactor pumping out hundreds of megawatts. But what happens when their service ends? How do you cut out the heart of a nuclear monster and survive a battle with invisible radiation that lasts for months? Temperatures here hit 14,000 degrees Fahrenheit. A mistake isn't measured in seconds, it's measured in centuries. In this video, you'll see the decommissioning process from the first cut to the last ton of melted metal, and find out what becomes of a submarine giant's armor. The process begins with the most dangerous stage, removing the spent nuclear fuel. The submarine is moved into a special enclosed dock. Around it, a real scientific laboratory unfolds. This is a battle against invisible radiation. It doesn't last days, it lasts months. Inside the reactor core are fuel assemblies. They've kept this monster alive for decades. Each assembly is a bundle of thin zirconium tubes about ½ an inch in diameter. Inside, uranium dioxide pellets. One assembly is 13 feet long. Weight, 660 pounds. The reactor holds 100 to 120 of them. They're removed using remote manipulators. Each assembly emits a lethal dose of radiation, 500 roentgens per hour at 3 feet. That'll kill a person in an hour. The assembly is lifted by a crane rated for 20 tons and lowered into a lead container. Container wall thickness, 10 inches of pure lead. Container weight, 17,000 pounds. Only lead stops gamma radiation. The containers are loaded into special rail cars with water cooling and shipped to temporary storage. This stage takes 3 to 4 months of continuous work. If you're interested in seeing how things built for war get taken apart, subscribe to the channel. Here we show you production processes hidden from view. Once the fuel's extracted, it's time for the reactor compartment. This is a massive section of the sub. Weight, 1,500 tons. Length, 33 feet. Diameter, 30 feet. Engineers don't dismantle the reactor piece by piece. Too dangerous. The metal itself is radioactive. Neutron flux from the operating reactor bombarded the steel for years. Iron atoms transformed into radioactive isotopes, so they cut out the entire compartment whole. They use oxyacetylene torches. Flame temperature 5,800 degrees Fahrenheit. Mix of acetylene and oxygen. Feed pressure 217 pounds per square inch. The torch burns through 3-inch thick steel in 10 minutes. They cut in a ring around the compartment. 2 cuts, forward and aft. You get a cylinder. All technological openings are welded shut with half-inch steel plates. Welding, electric arc, 1/4-inch diameter electrodes. Current, 350 amps. You get a sealed capsule. It's lifted by a 200-ton crane and loaded onto a barge. The barge is towed to a burial site. In Russia, that's Novaya Zemlya. In the US, Hanford site. There, the capsules are placed in concrete trenches 65 feet deep, covered with earth on top. They'll sit there 300 years until radiation levels drop to background. Decontamination is the longest phase. The reactor compartment's cut out and shipped off, but the work's just beginning. Decades of coolant circulation left their mark. Thousands of feet of primary loop piping, pumps, heat exchangers, steam generators, all of it contaminated. Radioactive isotopes soaked into the metal. That's induced radiation. Teams in protective suits scan every foot, hunting for hotspots, areas with elevated readings. They use DP5B dosimeters. Sensitivity, 0.01 milliroentgen per hour. Every pipe gets checked, every pump, every valve. Then chemical flushing begins. They run acid solutions through the primary loop piping. Sulfuric acid at 10% concentration. Temperature 140 degrees Fahrenheit. Pressure 115 psi. The acid dissolves the oxide film off pipe walls. Radioactive isotopes go with it. Solution gets collected in 13,000-gallon tanks, filtered through ion exchange resins. Radionuclides precipitate onto the resin. Resin gets incinerated at 2,200 degrees Fahrenheit. You get ash. Mix the ash with cement and pour it into concrete containers. That's Class 2 radioactive waste. Chemistry doesn't work everywhere. Valves, gate valves, filters, they dismantle those by hand. Teams of 3. Shifts last 30 minutes. Can't go longer, the dose accumulates. Every part gets packed in a lead box. Box weighs 265 pounds. Walls, 4 inches of lead. If contamination levels run too high, they encase the part in concrete right inside the hull. Special attention goes to the reactor's biological shield. Massive plates of lead and polyethylene. Lead layer, 6 inches thick. Polyethylene, 12 inches. Lead stops gamma rays. Polyethylene slows neutrons. Weight per plate, 4 tons. 8 plates total. They pull each one with a crane. Decontaminate with ultrasound. Frequency, 40 kilohertz. Power, 3 kilowatts. Ultrasound breaks down the oxide film. Then they rinse the plate with alkaline solution and dry it with hot air at 250 degrees. Only after thousands of air samples and surface swabs, when everything reads 0, they open the dock to regular workers. Now it's not a nuclear facility, it's just a complex steel structure. Cutting the hull. After decontamination, the submarine is ready for final dismantling. The submarine's hull isn't ordinary metal, it's an alloy built for war. It withstands water pressure at depths of 1,000 to 1,300 feet. That's 30 to 40 atmospheres. Hull thickness, 3 to 4 inches. A K29 grade steel. Tensile strength, 100,000 pounds per square inch. Regular cutters won't touch it. They use plasma torches. Plasma is ionized gas. An electric arc creates the temperature. Voltage, 300 volts. Current, 400 amps. Power, 120 kilowatts. Argon gets blown through a nozzle 1/8 inch across. Pressure, 90 pounds per square inch. Flow rate, 1 cubic foot per minute. The arc heats the argon to 15,000 degrees Fahrenheit. That's 1.5 times hotter than the surface of the sun. The plasma jet shoots from the nozzle at 670 miles per hour. That's the speed of sound. Under that stream, 4-inch thick steel melts in 5 seconds. The torch follows the marked line. Cutting speed, 8 inches per minute. Sparks and smoke fly from the torch. Flame height, 10 feet. Spark temperature, 1,800 degrees. The second tool, oxygen lances, a 10-foot steel pipe, 1-inch diameter. Inside, a bundle of steel rods, each about 1/6 of an inch thick. Pure oxygen flows through the pipe at 150 psi. Flow rate, 50 cubic feet per minute. The rods are ignited with an acetylene torch. They start burning in the oxygen. Steel burns. Massive amounts of heat pour out. Temperature in the burn zone, 6,900 degrees Fahrenheit. The lance burns clean through the steel, leaves a molten seam 2 inches wide, burn through speed, 20 inches per minute, faster than plasma. But it takes serious skill. You guide the lance dead perpendicular. Deviate more than 10 degrees and the burn's incomplete. Crews of 4. Protective suits made of Kevlar. Masks with number 13 filters. They block infrared and ultraviolet radiation. Without the mask, your retina burns in 1 second. They cut from bow and stern, working gradually toward the center. The hull gets cut into cylindrical sections, each section 20 feet long, 30 feet in diameter. Weight, 400 tons. Cranes rated for 800 tons lift the sections and stack them in the sorting zone. Metal sorting. Every hull fragment gets checked again with dosimeters. They're hunting for isotope traces in microcracks and weld seams. If the device clicks, the fragment gets isolated, sent for recleaning or special disposal. Only clean metal receives a safety certificate. It can leave the shipyard territory, then sorting by chemical composition. Steel grades HY80 and HY100. These are high-strength steels. Nickel content, 8%. Chromium, 2%. Molybdenum, 1%. These alloying elements are treasure for metallurgists. Nickel provides toughness. Chromium, corrosion resistance. Molybdenum, strength at high temperatures. Regular hull steel. AK-29 gets sent for remelting separately. Titanium parts, the sail, fairings, also separate. Titanium doesn't melt with steel. Different melting points. Titanium, 3,034 degrees Fahrenheit. Steel, 2,795. Copper alloys, wiring, heat exchangers, to non-ferrous metal. Aluminum alloys, bulkheads, ladders, to aluminum scrap. Reborn in fire. High-strength steel heads to the metallurgical plant. Loaded into an electric arc furnace. Capacity, 100 tons. 3 graphite electrodes, 24 inches in diameter. 600 volts, 60,000 amps. 36 megawatts of raw power. An arc ignites between the electrodes in metal. The arc zone hits 6,300 degrees Fahrenheit. Metal melts, becomes a liquid lake. The melt reaches 3,000 degrees. Melting time, 3 hours. Lab techs pull samples every 30 minutes. Analyze composition on a spectrometer. Adjust with ferroalloy additives. Precision matters. Carbon tolerance, plus or minus 0.05%. Nickel, plus or minus 0.1%. Finished melt pours into a ladle. The ladle weighs 200 tons. From the ladle, it flows into molds. Create slabs, steel plates. 6.5 feet by 20 feet. 10 inches thick. 23 tons each. Slabs get rolled into sheets or cut into rebar stock. Yesterday's warship armor plating becomes a river bridge support or a skyscraper skeleton. Steel that once withstood depth charges now holds up bridges. Metal doesn't die. It lives again. If you found this fascinating, hit that like button. Drop a comment. Did you know submarines get recycled for 300 years? Subscribe. We show you how the old dies and the new is born. Picture a metal lighter than plastic. Burns brighter than the sun itself. And you can pull it straight from seawater. Sound like science fiction? This is magnesium, the metal that revolutionized aviation, space exploration, and even your smartphone. Every year, humanity produces over 1,200,000 tons of this remarkable material. But few people know that behind an ordinary chunk of silvery metal lies technology worthy of science fiction. How does material stronger than steel and lighter than aluminum emerge from ordinary seawater or rock? You'll discover why magnesium burns at temperatures reaching 3,000 degrees, how it's extracted from the ocean floor, and why no modern aircraft can exist without it. Watch until the end. The finale will transform your understanding of what lightness and strength really mean. This is the story of the metal of the future, already here. The story of magnesium began in 1788 in a small English town called Epsom. A local farmer named Henry Wicker noticed something odd. His cows refused to drink water from a particular well. The water was bitter, but it had an amazing property. It healed. People from all around started coming to this spring. That's how a mineral was discovered, later named Epsom salt or magnesia. But this was just the beginning. Pure metallic magnesium was first produced by British chemist Humphrey Davy in 1808 through electrolysis. He passed an electric current through molten magnesium salt and got silvery drops of a previously unknown metal. The metal turned out to be remarkable. It was incredibly light yet strong, and most astonishing, it burned with a blinding white flame, brighter than any material known at the time. In the 19th century, magnesium was rarer than gold. Scientists produced it by the gram in laboratories for experiments. Everything changed when inventors realized something. Magnesium could create brilliant light. Early photographers fell in love with this metal. A flash of magnesium powder delivered such powerful light that you could take pictures even in total darkness. Picture this. The 19th century, a dark studio. A photographer ignites a pinch of magnesium powder and boom! A blinding flash illuminates everything around. That's exactly where the expression magnesium flash came from. But the real breakthrough happened in the 20th century when humanity mastered mass production. Magnesium turned out to be the ideal material for aviation. Lightweight, strong, easy to machine. During World War II, magnesium production skyrocketed tenfold. Military aircraft needed lightweight and durable parts, and magnesium became a strategic material on par with oil and steel. But where does this amazing metal come from? Magnesium is one of the most abundant elements on Earth. It's the 8th most common in the Earth's crust. But you won't find it in pure form. It's too chemically active and always bonded with other elements. The main sources of magnesium are dolomite and magnesite, rocks extracted through open-pit mining. The largest deposits are in China, Russia, Turkey, and North Korea. But there's another source, practically inexhaustible: the ocean. Every cubic mile of seawater contains about 3 million tons of magnesium. Imagine the scale. The world's oceans hold roughly 4 quadrillion tons of magnesium. That's enough to last thousands of years even at current consumption rates. That's exactly why many modern plants are built right on the coast. Why dig in the ground when you can draw from the ocean? Now let's dive into the actual production. There are 2 main methods for obtaining magnesium: thermal and electrolytic. Let's start with the thermal method, which is used when the raw material is dolomite or magnesite from quarries. First, the rock is crushed into small pieces, no bigger than a walnut. Then these pieces go into huge rotating kilns. Picture a steel cylinder the length of a football field, slowly turning. Inside, temperatures hit over 1800 degrees Fahrenheit. At that temperature, carbon dioxide burns off from the dolomite, leaving magnesium oxide, a white powder that looks like chalk. This powder gets mixed with coke and silicon, then pressed into brick-sized briquettes. These briquettes are loaded into special retorts, sealed steel vessels that can withstand extreme conditions. That's where things get really interesting. The retorts are placed into massive furnaces and heated to 2,200 degrees Fahrenheit. At this temperature, the chemical reaction begins. Silicon displaces magnesium from its compounds. But there's a problem. At this temperature, magnesium turns into vapor. Yeah, you heard that right. The metal evaporates, just like water in a kettle. The magnesium vapor rises up through the retort and enters a condenser, a specially cooled chamber. Here, the temperature drops sharply and the magnesium vapor condenses. Crystals of pure metallic magnesium grow on the cold walls. It's like frost on a window, except instead of ice, it's silvery metal. The process happens in a vacuum or in an inert gas atmosphere. Because magnesium is so reactive, it can ignite even in regular air at high temperatures. After several hours, they open the retort. Inside, an ingot of pure magnesium weighing about 22 pounds. It's warm, silvery, covered with a thin oxide film. Now let's break down the electrolytic method. This is exactly what they use when extracting magnesium from seawater. The process starts right on the ocean shore. Seawater gets pumped into massive tanks and treated with lime. The lime reacts with magnesium salts dissolved in the water, forming a white precipitate, magnesium hydroxide. This precipitate settles to the bottom. They collect it and rinse it. You get a white paste that looks like toothpaste. They treat this paste with hydrochloric acid, producing magnesium chloride, a clear solution with a bitter taste. The solution gets evaporated in enormous vats, yielding magnesium chloride crystals, white like coarse salt. These crystals are the key to obtaining pure metal. They load them into electrolytic cells, massive steel containers lined with refractory brick. Inside, molten magnesium chloride at 1300 degrees Fahrenheit glows orange like volcanic lava. A powerful electric current flows through the molten salt, thousands of amps. The magic of electrolysis begins. At the cathode, the negative electrode, droplets of pure magnesium form. They float to the surface because magnesium is lighter than the salt it's extracted from. A layer of liquid metal forms on top, which workers periodically collect with a special ladle. Picture this: a ladle scooping silvery liquid from the surface of a glowing orange melt. It's like skimming cream off milk, except the cream is molten metal at 1200 degrees Fahrenheit. The magnesium is poured into molds and left to cool. You get ingots weighing between 11 and 33 pounds each. They're silvery, lightweight. You can lift a 33-pound ingot with one hand. The surface quickly forms a thin oxide film that protects the metal from further oxidation. Without this film, magnesium would slowly oxidize even in air. Now we've got pure magnesium. But what do we do with it? The applications are vast, and all of them are impressive. Let's start with aviation and aerospace. Magnesium and its alloys are used to make aircraft fuselages, engine components, landing gear. Why? Because weight is everything in aviation. Every pound saved means less fuel and more payload. Magnesium alloys are 40% lighter than aluminum ones with comparable strength. A modern passenger airliner contains several tons of magnesium alloys. Spacecraft and satellites too. When you need to put cargo into orbit, where every pound costs thousands of dollars, magnesium is irreplaceable. The automotive industry has fallen in love with magnesium too. Engine blocks, transmission components, wheel rims, all made from magnesium alloys, especially in sports and racing cars where weight is critical for speed and handling. A single magnesium rim weighs half as much as a steel one with the same strength. Electronics, another massive area where it shines. Laptop cases, tablets, smartphones, cameras, often made from magnesium alloys. Why? Lightweight plus excellent heat dissipation plus strength. Your smartphone or laptop might be packing magnesium right now. Magnesium is also used to protect other metals from corrosion, so-called sacrificial anodes. They're installed on ship hulls, underwater pipelines, oil rigs. Magnesium oxidizes first, protecting the main steel structure. Global magnesium production sits at around 1.2 million tons per year. China cranks out about 85% of all magnesium. Russia, the US, and Israel, other major producers. Magnesium prices swing from $2,000 to $4,000 per ton, depending on purity and market conditions. That's cheaper than aluminum, but pricier than steel. And so, traveling from bitter water in an English well, through dolomite quarries and endless oceans, through the hellish heat of furnaces at 1200 degrees, and the cold of crystallization, magnesium emerges into the world. A metal lighter than plastic and stronger than many steels. This is the story of how humanity learned to transform rock and seawater into a material that lifts planes into the sky and sends satellites to the stars. Every time you board an aircraft, hold your smartphone or watch fireworks burning with blinding white flame. Remember, behind it all is magnesium, an ancient element we learned to tame just 200 years ago. A metal that taught us lightness and strength can go hand in hand. The metal of the future harvested from an infinite ocean that will serve humanity for thousands of years to come.
Are you ready to peer into a world where millimeters determine life and gleaming metal journeys from raw material to lethal precision? Picture this. Over 12 billion cartridges are manufactured worldwide every year for military, police, hunters, and sportsmen. And each one is the result of jewelers' precision engineering, where temperature, pressure, and form matter down to the last decimal place. In this video, we'll show you everything From selecting gunpowder and brass alloys to quality tests where muzzle velocity reaches nearly 900 meters per second. Brace yourself. This isn't just a story about bullets. It's a journey into the heart of modern manufacturing, where technology and science operate at the very edge of what's possible. Hundreds of millions of cartridges roll off factory production lines worldwide every year, and each one passes through quality control with micron-level precision. The primary material is brass, an alloy of 70% copper and 30% zinc. It's ordered in massive coils roughly 1.5 millimeters thick, weighing up to 2,700 kilograms. These coils are supplied by metallurgical plants. Upon arrival at the factory, the brass is unwound on a special platform and fed into a rolling mill. The metal's temperature at this stage reaches 315 degrees Celsius to make it more malleable. Next, the brass sheet is fed into a press line, a high-speed stamping machine that cuts out discs with lightning precision, so-called blanks. Their diameter is roughly 19 millimeters. The press operates at up to 250 strikes per minute. The resulting discs are heated to 430 degrees, essential for the next deep drawing process. They're immersed in lubricant and fed into a hydraulic press, where under pressure of up to 100 tons, the disc is formed into a primary case. This process repeats several times, each time drawing the case slightly longer and thinner. Each case after drawing is annealed, heated to 540 degrees to relieve internal stress in the metal. Otherwise, the case could crack during firing. It's then cooled in water and cleaned in an acid solution. Next comes calibration and weighing. Cases pass through a high-precision laser control system. Weight discrepancy means automatic rejection. Length, wall thickness, and even acoustic response are checked. Special sensors detect whether there are microcracks in the case. Finally, the case is trimmed to precise length, a groove is cut for the primer, and the neck is expanded. The next critical stage is primer installation. It's a small but absolutely vital component that initiates firing. The primer is miniature explosive. Inside a metal cup sits the primary detonator, typically based on lead styphnate. Before installation, primers are tested for sensitivity. On an automated line, each case passes through a priming station, where a mechanism inserts the primer into the rear of the case with incredible precision. Next comes gunpowder. The type depends on the cartridge's purpose. On average, one 223 Remington cartridge contains roughly 1.5 grams of powder. For comparison, a .45 caliber cartridge uses just 0.4 of a gram. Powder is measured automatically to 1/1000th of a gram. Excess or shortage means danger for the shooter and weapon. 1/10 of a gram discrepancy is unacceptable. Once the powder's in, it's time to install the bullet. Its material, shape, and mass depend on the task: hunting, military, sport. But installation happens with the same precision. The bullet is pressed under pressure into the case. Then the neck is crimped so it won't cop out during chambering. After this comes final calibration and visual inspection. Rejection rate at major facilities is under 0.3%. And only after all stages of inspection, calibration, and final weighing does the cartridge reach its ultimate phase, packaging. Packaging isn't just aesthetics, it's a matter of protection, identification, and logistics. Cartridges are automatically sorted into trays or fed to weighing lines, where batches are formed in 20s, 50s, or 100s. The cheapest option is plastic trays with heat shrink film. Military supplies are packaged differently, in zinc or steel containers with hermetic lids. Inside are inserts with anti-corrosion treatment, marking with caliber, batch number, and manufacturing date. On industrial lines, one shift packages between 100,000 and 300,000 cartridges. Individual factories operate 3 shifts 24/7, especially during periods of high demand. One packaging machine's output reaches 12,000 units per hour. In workshops with powder, primers, and explosives, there's anti-static flooring. This is special surfacing that channels electrostatic charge from human bodies or equipment into the ground to prevent sparks. Workshop humidity is also maintained at 40 to 60%, which reduces ignition risk. Workers wear special suits made from natural fabrics or anti-static materials. Wearing metal objects, watches, or jewelry is forbidden. Only certified specialists are permitted near powder or primer zones. Access is, naturally, biometric. People don't touch powder manually. Everything happens through sealed automated systems. Primer formation, explosive mixture dosing, case sealing, everything's maximally automated. Every 45 meters, there are powder extinguishers and sprinkler systems positioned. Personnel undergo mandatory drills every 3 to 6 months. All cases, bullets, and primers undergo visual, weight, and X-ray inspection. Rejects are sent to separate safe zones where they're disposed of or recycled. The factory is guarded like a classified facility. CCTV, armed security, inventory of every single unit. In 1998, in the United States, a powder manufacturing plant for sporting ammunition exploded due to storage regulation violations. The blast's force was equivalent to several tons of TNT. 4 workers were killed. Investigation revealed dozens of systemic violations. That's why safety at such factories matters more than the products they manufacture.
Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack, for decades. How does a 4 millimeter sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets, and I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes. It all starts in the raw materials warehouse, and the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport, chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts, with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part, forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method, shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting.
When all the parts are ready, assembly begins.
The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets.
After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick, and every fraction of that journey, someone's work, someone's inspection, someone's craft.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide?
starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer.
The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split and evenly distributes the load. That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse to later become part of furniture, houses, and ships.
The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets.
The world's largest source of recycled steel isn't born in deep mines, but in bustling cities. They call it the car's second gateway. It's the vehicle recycling industry, the industry that transforms car graveyards into the most efficient steel mines of the modern era. In the United States alone, more than 12 million cars vanish from the roads annually, beginning a remarkable journey. This isn't a story about the death of metal. It's a story about its immortality. How does steel, having completed its service, pass through fire and mechanical hell to be born anew? And what is the astonishing secret hidden in every old car that even its previous owner doesn't know? The answers will astound you. Behind every car rusting at the roadside lies a colossal $60 billion industry. This is a world where millions of old cars never truly die, they simply transform. This process provides employment for hundreds of thousands of people and deals a hefty blow to the costs of traditional metallurgy. Whilst iron ore represents a natural mine, limited and expensive, end-of-life vehicles are a man-made mine, practically limitless. Each recycling cycle saves up to 74% of the energy compared to the arduous mining of fresh ore from beneath the ground. That's enough to power a small town for an entire year. On average, up to 75% of each car's weight can be recovered, from steel and aluminum to glass and plastic, and returned to service. As a result, hundreds of millions of tons of materials are regenerated annually, continuing their journey as skyscrapers, household appliances, and even gleaming bodywork for the next generation of vehicles. When a motor car reaches the end of its service life, its story doesn't simply end. Rather, it's only just beginning. The vehicle is transported to the reception area of a recycling facility, a sort of purgatory for automobiles, if you will. Here, technicians, rather like pathologists, meticulously examine each patient. They record the vehicle identification number, year of manufacture, mileage covered, and general condition. Every car is photographed, assigned a unique tracking code, and all data uploaded into a digital system that will monitor its fate through each subsequent stage. Particular attention is paid to components that might still serve humanity: engines, gearboxes, alternators, and electronic elements. These organs are carefully extracted to feed a used car parts market worth billions of pounds. Remarkably, in the United States, thanks to an incredibly sophisticated system, over 95% of scrapped vehicles pass through this process. This makes motor cars the most recycled consumer product in the world, more efficiently recycled than paper or glass.
After reception, the vehicle is transferred to the detoxification area. The first and most crucial step is neutralizing the hidden danger. The lead-acid battery is immediately extracted from under the bonnet. Its recycling rate reaches nearly the ideal level of 98%. Lithium-ion packs from hybrid and electric cars require far stricter procedures and are sent to specialist facilities where they're dismantled almost entirely by hand. Only then is the electrically isolated vehicle lifted onto a platform for complete draining. Special installations resembling giant syringes pierce the tanks and pipes, pumping out all fluids: residual petrol, engine and gearbox oil, and air conditioning refrigerant. A written-off car still contains dozens of liters of flammable and toxic materials. Remarkably, nothing goes to waste here. Most extracted fluids are filtered and used to fuel the plant's own equipment, creating a nearly closed energy loop.
Once all the fluids have been drained, the car transforms into a lifeless steel skeleton, and its anatomical dismantling begins. The wheels come off first. Old tires, which would otherwise decompose for centuries in a landfill, are sent for shredding into rubber crumb for tarmac and safe surfacing for children's playgrounds. The steel and aluminum discs go straight for remelting. Next comes the glass. Specialized robots with diamond cutters remove the windscreen and side windows. Then the doors are taken off. The steel frames are cut away, whilst the complex innards, electric motors, speakers, and miles of wiring, are stripped separately to extract valuable copper. After that comes the interior: seats, dashboards, and carpeting. Finally, the climax arrives: the extraction of the car's heart and soul. The engine and gearbox, the heaviest and most valuable units, are carefully lifted out using hoists. Some will be restored, the genuine high-mileage survivors, and sold on. Others will be dismantled down to the last bolt to extract precious metals from catalytic converters: platinum, palladium, and rhodium. Before a car enters the final chapter of its life, it awaits harsh yet necessary procedures. Everything surplus is stripped away. Enormous mechanical arms, fitted with hydraulic shears capable of slicing through steel beams with forces of dozens of tons, tear off what remains of the doors, rip out exhaust systems from their roots, and crush radiators like paper cups. Plastic bumpers, upholstery remnants, and foam are cast aside. This stage serves as a crude filter, removing anything that might contaminate the pure steel. After just a few minutes of brutal yet effective cleaning, nothing remains of the car but its pure essence, a sleek steel shell. It's now sent to a hydraulic press. Under crushing force ranging from 150 to 200 tons, as though a blue whale had stepped upon the vehicle, the chassis is compressed into a compact metal block, merely 1/10 of its original size. Once the structure's been compressed, these dense steel blocks, rather like giant sugar cubes, are fed into the maw of a genuine monster, a high-performance shredding machine. This is the mechanical heart of the entire line. Inside its chamber, massive steel rollers fitted with hardened steel teeth rotate in opposite directions. With an ear-splitting roar that shakes the ground, they seize the compressed block and tear it to shreds. Within seconds, what was once a car occupying an entire parking space transforms into a stream of homogeneous scrap metal fragments roughly the size of a fist. A modern industrial shredder can process up to 150 tons of steel per hour. That's hundreds of cars every single day. After shredding, this mixture of metals and nonmetals travels along the sorting line. Powerful magnets suspended above the conveyor pluck all the steel from the stream, whilst eddy currents, creating an invisible field of force, deflect the lighter aluminium and copper to one side. What was once a car's skeleton is now fed as pure steel billets into the electric arc furnace. Here, a fiery rebirth awaits. Massive graphite electrodes descend into the metal mass, unleashing currents of tens of thousands of amperes, creating a dazzling arc resembling artificial lightning. Within minutes, the internal temperature soars beyond 1,600 degrees Celsius, transforming solid scrap metal into a raging torrent of molten steel. Lime and flux are added to this fiery ocean, acting like chemical sponges, absorbing all remaining impurities and forming a layer of slag on the surface. From a chaotic mass of old car parts emerges a shimmering sea of pure molten steel. This blazing current is immediately directed to the continuous casting line, where it flows into water-cooled molds, solidifying and forming long, glowing blocks or billets. The moment it leaves the furnace, the red-hot glowing steel blocks head straight to the hot rolling mill. Here, dozens of massive rollers, spinning at tremendous speed, continuously press and stretch them, giving them a new form, whether that's a panel for a future motor car or reinforcement bars for a skyscraper. The freshly rolled steel must be cooled, but this must be done in a controlled manner. Spray nozzles envelop its surface in a white mist, rapidly reducing the temperature. Once the steel has cooled, each coil undergoes rigorous inspection. Ultrasonic sensors scan for any hidden internal cracks, invisible to the naked eye. From fiery glow to stable strength, this is how steel is reborn. Every finished motor car feeds a multi-billion-pound industry, proving that recycling isn't merely an environmental solution, but also a hidden pillar of the modern economy. And the secret we mentioned at the start is simple. In every new car, in every skyscraper, in every bridge, there lives a part of a motor car that once traveled our roads. Metal doesn't die, it simply awaits its hour to return. Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to 3 products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers, or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed two electrodes, a positively charged anode and a negatively charged cathode. Now, to these electrodes is applied a direct electrical current of colossal force. And here, the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now, let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. But they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained 3 substances, chlorine, hydrogen, and caustic soda, and they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled, then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal, because leakage of this gas is deadly dangerous. And what about our byproducts? They're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain three extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business.
Every hour across the globe, dozens of nuclear reactions. But only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead. Watch until the end, because the finale will change how you see the modern world. Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping. While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction.
But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual: immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload. A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around the sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical. If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake. This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations. Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes: testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the U.S. conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore, but a miniature star created by humans. The explosion wiped out an entire island.
In the 1960s, testing became routine. The US tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the US declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Every year, the world produces over 5 million tons of structural steel, and almost all of it is born from rusty scrap. Old cars, dismantled ships, demolished bridges get melted down and transformed into I-beams, the steel backbone of modern cities. From the outside, it looks simple, a piece of metal with that distinctive I-shaped profile. But this shape is the result of engineering genius, allowing a single beam to support loads of several hundred tons. A skyscraper being built somewhere in the world right now might contain a piece of armor plating from a warship, melted down and born again. This isn't just metal, it's history, sealed in steel. How does a mountain of rust become a precision structure with tolerances measured in fractions of a millimeter? And why is every modern building taller than a few stories impossible without this unassuming component? Stick around till the end. There's a moment we'll show you that's almost never seen publicly. The genius of the I-beam is in its shape. When it bends, the main load hits the top and bottom edges of the cross-section. That's where most of the steel lives, in those horizontal flanges. The thin vertical web in the middle, it just holds the flanges apart at the right distance. This gives you maximum strength with minimum weight. And that's exactly why this profile shows up everywhere you need to span a gap without wasting material. If you rolled that same volume of steel into a flat rectangle, it'd hold a fraction of the load. That I-shape isn't about aesthetics, it's math. One properly installed heavy I-beam can handle hundreds of tons. Picture a column of fully loaded semi-trucks standing on a single piece of steel. That's the real power of shape. But this story doesn't start in some gleaming factory. It starts at a massive, noisy yard that looks like a graveyard for metal dinosaurs. This is a scrap metal depot. Mountains of old cars, sliced up railroad cars, construction wreckage, and industrial junk, all waiting to be reborn. If stories about the hidden life of metal grab you like this, subscribe to the channel right now and hit that bell so every new episode lands straight in your feed. A giant crane with a powerful electromagnet descends onto this pile, and with a metallic screech, tons of old iron stick to it. This scrap is the main ingredient of the entire production process. It's loaded into a massive steel basket and sent to the melting shop, where a fiery baptism awaits. Steel is the absolute champion of recycling. The recycling rate for structural steel reaches 98%. That means practically all the metal from demolished buildings, old bridges, and scrapped ships returns to production. On average, a new I-beam is 90% recycled metal. A skyscraper being built today might contain a piece of a car from the 70s, a railroad rail from the 30s, and armor from a World War II ship. This isn't just a piece of steel, it's compressed history, remelted for new service. This is the special magic of manufacturing that almost never gets talked about. The steel cycle is virtually infinite, and each generation of cities passes its metal to the next. Every year, the US alone produces over 5 million tons of structural steel, and most of it, I-beams. That scale is hard to wrap your head around, so let's try. The steel in the Golden Gate Bridge weighs about 83,000 tons, which means American mills produce enough beams in 1 year to build more than 60 of those bridges. 60 Golden Gate bridges every year. And that's just one country. The heart of the mill is the electric arc furnace, a giant bucket the size of a small house where scrap metal gets dumped with a deafening roar. The sight alone is incredible, tons of twisted iron crashing inside, filling the bucket to the brim. From above, 3 massive graphite electrodes descend into the furnace, each one as thick as an old-growth tree. The operator flips the switch. An electric arc flashes between the electrode tips and the metal, an artificial lightning bolt striking with colossal force. The floor fills with a deep, ear-splitting roar, and the light from the arc is so bright it blinds you even through protective glass. The temperature inside instantly rockets to 3,000 degrees Fahrenheit. The metal doesn't stand a chance. It starts melting, transforming into a boiling, blinding lake. Special additives get thrown into this molten bath: manganese, silicon, sometimes chromium or nickel, to create the exact grade of steel needed. Strong yet flexible, able to withstand massive loads without shattering like glass. The entire melting process takes 40 to 60 minutes. And in that time, tons of rusty junk completely transform into uniform liquid metal. Once the steel's ready, it needs to go from liquid river to something solid. The molten metal gets poured into a continuous casting machine. Glowing liquid flows into a special water-cooled copper mold. Passing through it, the outer layer of steel solidifies, forming a thin shell. From there, this still semi-liquid billet continuously gets pulled downward, passing through a water spray zone where hundreds of nozzles shower it with water, forcing it to solidify completely. Out of the machine crawls an endless, red-hot, massive steel billet, square or rectangular in cross-section. This is called a bloom. Automatic cutters hiss as they slice off pieces to the right length, 20, 25, 30 feet. This is our blank, the chunk of dough we're going to shape into a beam. Looks like an ordinary rectangular bar. No hint of the form it'll take in just a few minutes. These hot but now solid blooms head to the next furnace, the reheating furnace. Think of it as a giant tunnel with flames roaring inside. The blank creeps slowly through, and its temperature climbs back to the perfect working state, around 2200 degrees Fahrenheit. It becomes plastic and soft, like clay, ready for the most critical step, rolling. The quality of this heating determines just how precise and uniform the final profile will be. And now, the real spectacle begins. The bloom, heated to a blinding orange glow, rolls out of the furnace and enters the rolling mill. This is a series of gigantic steel rollers, like enormous rolling pins positioned one after another. But these rollers aren't flat. They have special grooves or calibers whose shape gradually approaches that of an I-beam. The bloom crashes into the first pair of rollers. They squeeze it with incredible force, thousands of tons, making it slightly thinner and longer. At the exit, the next rollers catch it, compressing it at a different angle and starting to form the flanges and web of the future beam. Step by step, passing through dozens of these roller pairs, the shapeless bar visibly stretches and takes on the familiar I-beam profile. A glowing chunk 20 feet long extends into a fiery ribbon stretching several hundred feet. The entire shop fills with thundering noise, the screech of metal, and the hiss of water cooling the rollers. This is one of the most powerful industrial spectacles you can witness with your own eyes. When the beam emerges from the final finishing roll, it already has perfect shape and dimensions, accurate to within 1/10 of a millimeter. Hot, long, Like a fiery serpent, it travels along a roller conveyor to a massive cooling table. This giant grid is where the beam slowly cools down, releasing its heat to the air. This process can't be rushed. Cooling too quickly creates internal stresses in the metal that can later lead to deformation or microcracks, invisible from the outside. During cooling, the metal shrinks slightly, and sometimes the beam can warp just a bit. This is normal and predictable. Engineers account for this in the manufacturing process. To correct any deviation, the cooled beam is sent to a straightening machine. It runs the beam through a system of rollers that press with calculated force and squeeze out any deviation from straightness. What comes out is a perfectly straight steel profile, ready for final operations. Now we've got a perfectly straight beam, but it's not ready to ship just yet. Time for the finishing touches. First, they cut it to the exact lengths the customer ordered. Giant circular saw blades about 6.5 feet across do the job. With a deafening roar and a shower of sparks, the saw slices through thick steel in just seconds. Then, every beam goes through rigorous quality control. Inspectors check the geometry, while ultrasonic equipment peers inside the metal, making sure there are no cracks or internal defects. Only after that does the beam get its markings, basically a birth certificate with info on the steel grade, size, and batch number. Standard beams range from a few inches tall to almost 3 feet. But there are real monsters, so-called super heavy sections used in the most critical joints of skyscrapers. These beams stand over 4 feet tall and weigh up to 1,200 pounds per foot of length. Think about that. Every foot of one of these beams weighs as much as 3 grown adults. Standard lengths run 60, 80, sometimes even 120 feet. A single beam weighs as much as a battle tank. This is it. Born from rust, passed through fire and thousands of tons of pressure, it becomes the silent steel backbone of a building that'll stand for centuries.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does 2 crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show, centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick.
It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture. Depending on exactly how the log was cut before slicing, you can get different types of patterns, radial, tangential, mimicking the look of solid plank. Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting. Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work, because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery. The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log. Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer. Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history,
one that lived for decades or centuries and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Imagine a river of white-hot metal as bright as the sun, born inside a giant furnace, melting everything in its path. But did you know that to create 1 ton of iron, you need almost 2 tons of rock and coal? It seems like alchemy. Hundreds of kilograms of oxygen and impurities vanish from dirty ore, leaving only pure metal behind. In the US, just a handful of these furnaces produce over 25 million tons a year, enough to build 250 aircraft carriers. And yet, there is a secret hidden within this story, one that will only be revealed to those who watch until the very end. It all begins deep in a quarry, where iron ore is mined. This isn't metal, but reddish-brown rock that looks like rusty earth. The iron is tightly bonded with oxygen, and the primary mission is to break that bond, liberating the metal within. Along with the ore, 2 other key ingredients for this infernal recipe arrive at the plant. The first is coke, a specially processed form of coal. It's baked in an oxygen-free oven to remove all impurities, resulting in pure, porous carbon that burns with incredible heat. In our process, coke is both the fuel and the main chemical agent. The third ingredient is limestone, a common rock. Its role? It's the cleaner. When heated, the limestone will act as a magnet for all the waste, collecting it into a separate mass. Now, let's go to the plant to meet the hero of our story, the blast furnace. It's a tower over 30 meters high, lined entirely with fireproof brick and wrapped in a network of pipes. This tower never sleeps. It runs continuously 24 hours a day, sometimes for years without stopping. It is a giant stomach that must be constantly fed. From the top, using a special skip hoist that looks like a small rail car, our ingredients are charged into the furnace. Not just thrown in, but layered like an industrial lasagna. A layer of coke, then a layer of iron ore and limestone, another layer of coke, and so on. To get 1 ton of liquid iron, you need to load almost 2 tons of raw material into the furnace. This figure includes the iron ore, the coke, and the limestone. It shows just how efficiently a blast furnace works as a giant filter. It takes nearly 2 tons of rock and coal, burns away everything unnecessary, and yields 1 ton of pure, concentrated metal. This is true industrial alchemy. Once the furnace is fed, the heat is turned up. At the bottom of the furnace are special nozzles called tuyères. Through them, air is blasted in under immense pressure, superheated to 1100 degrees Celsius. This hot blast ignites the coke, causing it to burn with incredible ferocity. The entire mass of materials loaded from the top begins its long journey down through zones of increasing temperature. First, in the upper section, hot gas is rising from below dry and preheat the ore. A little further down, the chemistry begins. The burning coke reacts with oxygen to form carbon monoxide. And this carbon monoxide is our master thief. It greedily rises, meets the iron ore, and starts stripping away the oxygen atoms, leaving pure iron behind. About halfway down, the temperature becomes so intense that both the iron and the impurities begin to melt. This is where our cleaner, the limestone, comes into play. It decomposes and starts to bind with all the unwanted elements, forming a light, molten mass called slag. At the very bottom of the furnace, in its heart, known as the hearth, a lake of 2 unmixable liquids forms. At the very bottom, being heavier, lies the pure molten iron. And floating on top, like oil on water, is the lighter molten slag. Every few hours, it's time for the tapping. A special machine, like a huge drill, pierces a hole in the fireproof lining of the furnace, first for the slag. A thick, bright orange river of molten rock erupts with a hiss. Once the slag is drained, the main event begins. The drill opens another hole slightly lower down, the iron notch. And from there, with a roar and a blinding glare, a torrent of molten metal is unleashed. It isn't orange, it's a brilliant white gold, so bright it's painful to look at without special glasses. The heat radiates from it, a physical force you can feel on your skin from dozens of meters away. This dazzling river of metal, throwing off fountains of sparks, flows down a long refractory channel into a huge mobile ladle shaped like a giant cigar on wheels, known as a torpedo car. This torpedo can hold several hundred tons of liquid metal and, like a thermos flask, keeps it hot while it's transported to the next stage. What we have created in the blast furnace is called pig iron. It contains a lot of carbon, which makes it very brittle. When the metal cools in the molds, it solidifies. After the mold is broken, a finished cast iron product is revealed. And so, from a cold, red rock through the fiery stomach of the blast furnace where chemistry and heat work their magic, this heavy, reliable, and durable material is born, ready to serve us in our daily lives. Each year, blast furnaces in the United States produce roughly 30 million tons of iron. It's a number so vast, it's hard to comprehend. Let's try. The average Nimitz-class aircraft carrier weighs about 100,000 tons. This means that in 1 year, American plants produce enough iron to build a fleet of 250 of them. Or to put it in more grounded terms, if we take the weight of an average passenger car, that's enough metal to make over 12 million vehicles. An entire automotive nation born in the fire of the blast furnaces in a single year. There are only about 15 blast furnaces currently operating in the entire country. We are not talking about thousands of small plants, but a small number of true titans. This means each of these towers is an incredibly productive monster. The average blast furnace in the U.S. produces over 5,000 tons of iron every single day. Over 90% of all pig iron produced in blast furnaces is not the final product. It is just the first step. This hot, carbon-rich metal is essentially the raw material for making steel. It is transported in torpedo cars to the next plant, where, in oxygen converters or electric furnaces, the excess carbon will be burned off, turning brittle iron into strong, ductile steel. So these 25 million tons of iron are the foundation from which skyscrapers will rise, bridges will be built, and cars, ships, and even simple tools will be made.
Without this metal, there'd be no electronics, no smartphone in your pocket, no computer on your desk, no satellite in orbit. Every second, millions of microchips are being soldered worldwide, and they all depend on tin. The metal that 5,000 years ago launched humanity into the Bronze Age today connects transistors and processors. The oldest metal of civilization became the foundation of the digital revolution. How do gray rocks from the jungles of Malaysia become the silvery metal that flows from your soldering iron? You'll learn why tin doesn't rust, how it changed the course of human history, and why modern industry would collapse without it. Watch until the end. The finale reveals what's behind every microchip in your phone. This is the story of a metal that survived millennia and remained irreplaceable. Tin's story predates writing itself. Around 5,000 years ago, in the 3rd millennium BC, someone accidentally mixed copper with tin. The result? An alloy harder and stronger than both metals, bronze. It changed everything. The Bronze Age began, an entire civilizational era named after a tin alloy. Bronze swords, axes, armor were sharper and lasted longer than stone and copper. Armies with bronze weapons conquered continents. There was one problem. Tin was rare. Copper could be mined everywhere, but tin only in a few places on Earth. Cornwall in Britain, Bohemia in Central Europe, the mountains of Afghanistan. Expeditions traveled thousands of miles for tin. Phoenician traders sailed to Britain's foggy shores across the entire Mediterranean just for tin. The metal was valued more than gold. Whoever controlled tin deposits controlled military power. Civilizations rose and fell depending on access to this silvery metal. In the Middle Ages, tin was used to make tableware. Tin cups, plates, mugs. Tin doesn't rust and doesn't give food a metallic taste. Rich people ate from tin, poor people from wood or clay. Tin soldiers became a favorite toy for children in the 19th century. They were cast by the millions. But a strange danger lurked. At temperatures below -13 degrees Celsius, with tin, something miraculous happens. The silvery metal starts turning into gray powder. This is called tin pest. The crystalline structure reorganizes. The metal crumbles. During cold winters, tin buttons on soldiers' uniforms turn to dust. Tin pipes and church organs inside unheated cathedrals disintegrated. Napoleon lost his army in Russia, not just from the cold. Tin buttons on soldiers' uniforms crumbled. Clothing fell apart. Tin past played its role in history. Modern tin is treated with additives that prevent this transformation, but pure tin in freezing temperatures still turns to powder. Where does tin come from today? Tin is a rare element. It makes up just 0.02% of Earth's crust. The primary tin mineral is cassiterite, tin oxide, dark brown or black crystals, incredibly heavy, density almost 7 grams per cubic centimeter, heavier than iron. The largest deposits are in Southeast Asia, Indonesia, Myanmar, Thailand, Malaysia. They account for about 70% of global production. There are deposits in China, Peru, Bolivia, Australia. Tin is extracted 2 ways: open pit mining in quarries, or washing from placer deposits. Placers form when cassiterite gets weathered out of rock by rivers over centuries and accumulates in valleys. Heavy crystals settle to the bottom. Lighter rock gets carried away by the current. In Malaysia and Indonesia, entire islands are made of tin-bearing sands. That's where most of the world's tin comes from. Then begins the dramatic process of transforming dark stone into silvery metal. Tin mining from placer deposits uses giant dredges. Picture a floating factory, a steel ship with a massive pipe that descends to the bottom. At the end of the pipe, a cutter head with teeth rotates. It tears into the bottom sand, grinds it up. Powerful pumps suck up the mixture of sand and water, slurry, and lift it to the surface. The ship has washing equipment installed, a system of flumes, screens, and centrifuges. The slurry flows down inclined flumes lined with special mats. Light sand washes away with water, while heavy cassiterite crystals get trapped in the mat fibers. It's like gold mining, except instead of gold, it's tin. Periodically, the mats are removed and shaken out. You get a concentrate, dark sand containing up to 70% cassiterite. The rest is impurities from other minerals. This concentrate is re-washed on special tables, blown with air to separate light particles. The final concentrate contains about 75% tin oxide. It's dried and shipped to the smelting plant.
At the plant, cassiterite is reduced to metallic tin. The concentrate is mixed with coke, carbon, and loaded into a reverberatory furnace. It's a massive furnace, the length of a bus, lined with refractory brick. Inside, temperatures reach 2,400 degrees Fahrenheit. Natural gas or fuel oil burns, flames reflect off the furnace roof and heat the mixture from below. At this temperature, carbon strips oxygen from the tin oxide. Cassiterite is reduced to metal. Molten tin collects at the bottom of the furnace, a silvery pool glowing orange from the heat. Tin's melting point is just 450 degrees, one of the most easily melted metals. The molten metal is periodically tapped through a tap hole, an opening in the furnace's sidewall. Silvery metal flows into ladles, but this isn't pure tin yet. It contains impurities: iron, copper, lead, arsenic. Refining is needed, purification. The molten tin is heated to 750 degrees and blown with compressed air. Impurities oxidize and float to the surface, a slag. The slag is skimmed off, the blowing repeated, several times over. Pure tin gets poured into molds, creating ingots weighing about 66 pounds each. Silvery white, shiny. Tin is incredibly soft. You can scratch it with your fingernail. But it has this amazing property. It doesn't oxidize in air. More precisely, it forms this ultra-thin oxide film that protects the metal from further corrosion. That's why tin cookware lasted for centuries. Today, most tin doesn't go into cookware, it goes into electronics. 70% of global tin production is used for soldering. Solder is an alloy of tin with lead or silver. The melting point of solder is around 400 degrees Fahrenheit, low enough that it won't damage electronic components. When you're soldering a microchip to a circuit board, the solder melts, flows into the gaps, cools down, and forms a solid electrically conductive connection. Without tin, assembling electronics would be impossible. Every smartphone contains thousands of soldered connections. Every computer motherboard, tens of thousands, all held together by tin. Tin is also used for tinning, coating other metals with a thin layer of tin. Tin cans, they're actually steel, just coated with tin inside and out. A layer of tin just a few microns thick protects the steel from rust and prevents food from contacting iron. Making tin plate, that's the second largest use of tin. Tin alloys are used in bearings, Babbitt metals, alloys of tin with copper and antimony. They're soft, lubricate well, handle heavy loads. Organotin compounds serve as stabilizers in PVC plastic production. Global tin production runs around 350,000 tons per year. That's tiny compared to steel or aluminum. But tin, it's a strategic metal. Without it, the electronics industry grinds to a halt. Tin prices hover around $25,000 per ton, 10 times more expensive than aluminum. Tin reserves are limited. Accessible deposits will last maybe 30 years at current extraction rates. That's why tin gets actively recycled, recovered from electronic scrap during disposal.
Here's something interesting. Tin is one of the few metals we actively recycle. Electronic waste recycling has become an entire industry. Old circuit boards from computers, smartphones, and TVs get collected and shipped to specialized facilities. There, the boards are shredded, treated with chemicals, or heated. The tin dissolves or melts out, then gets extracted and purified. From 1 ton of electronic waste, you can recover up to 22 pounds of tin. This is economically and environmentally profitable. First, it reduces the strain on natural deposits, which aren't that abundant anymore. Second, you don't need to spend energy on mining and processing ore. Tin recycling requires 10 times less energy than primary production. In developed countries, up to 30% of tin comes from recycled materials. Japan, which has no deposits of its own, recycles up to 50%. And
And just like that, traveling from dark cassiterite crystals in tropical placer deposits through the hellish heat of furnaces at 1300 degrees and countless purification stages, tin emerges into the world, civilization's most ancient metal, now the backbone of modern electronics. A metal that 5,000 years ago gave humanity bronze and empires, and today connects billions of transistors and processors. This is the story of how a rare element survived millennia without losing its value. What's more, it became even more critical. Every time you power up your smartphone, computer, or any electronic device, remember, inside, thousands of tiny droplets of tin hold microchips together. Without this soft silvery metal, there'd be no internet, no satellites in space, no artificial intelligence. Tin, the silent hero of the technological revolution, the metal that bridges past and future. From bronze swords of antiquity to microprocessors of today. 5,000 years of service to humanity. And this isn't the end. It's the continuation of a metal story that never goes out of style.
In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this, an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. (1946). World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions. But the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution. Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The 90s. The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how legends of the sky die. The process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise, though for the machine it's more like a waiting hell. Davis Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system: engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2, an organ donor. Everything valuable gets stripped out. Category 3, my complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids. Fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this. Hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration, $15 million per airframe. That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. $4,200 aircraft sit at the Boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The Boneyards become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently.
If you want to see what the industrial edge of the world looks like, come to Ecatepec. This suburb of Mexico City won't greet you with mariachis or cocktails on the beach. Here, the air is thick with exhaust fumes from old Volkswagen Beetles, and the mountains all around are shrouded in gray smog. But it's right here, among the dusty streets and endless chaos, that what Mexicans call their quiet revolution is happening. I'm standing at the gates of the Granutech factory. There's a pebble stuck in my right shoe, and in my mouth, the aftertaste of cheap pork tacos and dust. But ahead lies a black hell that's becoming this country's salvation. Mexico has a problem. Nope, scratch that. Mexico is facing a catastrophe. Every year, over 40 million tires get dumped here. Most end up in canyons, rivers, or just vacant lots, where they're burned, poisoning the air with dioxins. For Mexico City, a city already choking in its own basin, this is like slow poison. But there's another curse: the roads. In Mexico City, they're not just bad, they're midge. Thanks to constant earthquakes, soil subsidence, and tropical downpours, the asphalt here cracks faster than you can say gracias. Traditional bitumen gets brittle under the scorching high-altitude sun and washes away with the first rain. We decided to cross these two problems so they destroy each other, Carlos tells me, an engineer at the plant wiping sweat from his brow with an oil-stained hand. His eyes shine with pride, and I get why. We step inside. There's none of the sterility of American labs here. This place thrums with raw energy. Stage 1. Intake. Massive trucks, rusted and beaten down by life, dump thousands of tires right into a dirty yard. It's a depressing sight, whole mountains of black rubber, reeking of sun-scorched burn. But the second they hit the conveyor, the magic begins. The Granutech shredders are monsters. They don't just cut, they tear. The sound's like a giant iron beast chewing bones. Vibration comes up through the floor, hammers your legs, makes your teeth rattle. There's no room for conversation here. We're communicating with hand signals. I watch a tire from a massive truck get shredded into ragged chunks in seconds. Here, unlike those sterile European factories, you see every drop of the worker's sweat. They're hand sorting whatever the magnets missed. It's dirty, heavy, honest work. The dust is so thick that sunlight cuts through it in yellow beams. We move to the fine grinding zone. Here, the rubber passes through a cascade of mills, getting finer and finer until it becomes rubber flour. This is the secret ingredient. Carlos grabs a handful of this black crumble and holds it out to me. It's warm, almost hot. "This isn't trash," he shouts in my ear. "This is flexibility. This is what keeps the asphalt from cracking when the ground under Mexico City shakes again." Mexicans are proud of this technology, and they have every right to be. Roads with added old tires last 3 times longer. They're not afraid of water because rubber repels moisture, preventing it from seeping into the pores and destroying the foundation. Plus, these roads are way quieter. Mexico City is one of the noisiest cities on the planet, and every decibel that the rubber highway absorbs is a blessing. If the shredder is the brute force of the Granutech plant, then the bitumen modification shop is its devious and dangerous brain. We leave the noisy yard and climb iron staircases to a platform housing gigantic mixing tanks. Here, the air changes. Instead of dry rubber dust, your lungs fill with a heavy, oily mist. It's the smell of hot bitumen mixed with the sweetish scent of heated polymers. Rising from the center of the platform is the reactor, a massive steel thermos where real alchemy happens. Temperature here holds steady at 360 degrees Fahrenheit. This is the critical threshold. Drop below it and the reaction won't start. Go above it and the bitumen will rapidly oxidize and lose its properties. I watch as an automated auger begins feeding that same black flour, fine rubber crumb no bigger than a 32nd of an inch, into the scorching night black bitumen. The moment the crumb touches the molten liquid, a physicochemical marvel begins. You can't see it with your eyes, but the sensors on the monitor show it. The viscosity of the mixture starts climbing fast. The rubber doesn't simply melt because the rubber in tires is vulcanized. It can't just melt like ice. Instead, adsorption happens. The rubber particles start drinking the light petroleum fractions from the asphalt. A rubber particle swells to 2 or 3 times its original volume. It balloons up, becoming soft and elastic, a gel-like structure. Inside the reactor, high-speed mixers are working, literally grinding this swollen rubber into the asphalt structure. This isn't 2 separate things anymore. This is modified binder. "Watch the gauge," Carlos shouts, pointing at the instrument. "Pressure's climbing because the mix is getting thicker than honey." At the molecular level, devulcanization is happening. Some of the sulfur bonds in the rubber break down, and the polymer chains of the rubber intertwine with the asphalt molecules. They create a new network, a kind of reinforcement at the micro level. This network is the secret to permanence. Now, let's compare. Regular asphalt? It's rocks glued together with pure bitumen. Under Mexico City's intense sun, it softens. Then, at night, when it cools down, it hardens and becomes brittle. Over time, it turns into a dry shortbread cookie. All it takes is one heavy truck rolling over that surface and microcracks appear. Water gets in, freezes, or just washes away the base, and voila! You've got another pothole where your road used to be. Granitec's rubber asphalt works like a tough rubber tile. When a truck presses down on this asphalt, it doesn't crack. It deforms and, here's the key, bounces back to its original shape. That's called elastic recovery. We walk up to the discharge valve, where Carlos draws some of the finished mix into a metal container for testing. As it cools slightly, he stretches it like rubber. Regular bitumen would just tear apart, but this one pulls into long strands, bounces back, and retracts again. Right now, before our eyes, tons of this black mass pour into the dump truck bed. The temperature's still holding around 320 degrees. The mix smells like power and progress. This truck's heading to the outskirts of Ecatepec, where tomorrow morning, Mexicans will drive to work on a new road. A road that won't fear the Texas sun, torrential rains, or heavy buses. This is the real triumph of Granutec. We took the toughest trash, ran it through a 180-degree inferno, changed its chemical nature, and turned it into the foundation for safe travel. Here, on this platform, surrounded by steam and the thundering of iron, you get it. The future doesn't have to be clean and white. Sometimes it's black, sticky, and smells like hot rubber. If you found it fascinating how old tires transform into the roads of tomorrow, smash that like button on this video. Drop a comment if you know other amazing ways to recycle waste, and subscribe to the channel to keep discovering the technologies reshaping our world right now.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end.
The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go.
Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood.
In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead-coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries.
Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal.
Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off.
The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible. But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed.
Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that, traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history. A metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Every year, shipyards launch massive icebreakers and cruise liners, vessels weighing tens of thousands of tons, capable of operating for months in the planet's harshest seas. But few realize their engines are no longer inside the hull. Engineers took a radical step. They moved a power plant generating over 22 megawatts, that's more than 30,000 horsepower, and dropped it directly beneath the ship's bottom in a sealed steel pod weighing 320 tons. That's the weight of 2 fully loaded Boeing 747s. Inside that pod, a rotor misalignment by a fraction of a millimeter can shred bearings and destroy the entire drive system in just days. Watch this video to the end, and you'll discover how this underwater power plant is built, what installation mistake gets permanently hidden beneath the waves, and why this invisible enemy can obliterate a ship weighing thousands of tons in a matter of days. At first glance, it looks like a massive metal tail bolted to the ship's bottom. But inside, a full-blown electric motor. They don't mount it in the engine room like they did for decades. Here, it's the opposite. They drop the motor straight into the water, seal it tight in a steel shell, and make it work right there in the ocean. For years, no repairs, under constant seawater pressure. That's exactly why this thing's treated almost like a submarine. The idea of moving the engine outside the hull showed up relatively recently, even though engineers have been thinking about it for decades. Back in the mid-20th century, shipbuilders were trying to ditch the long shafts, gearboxes, and complex mechanical drives that ate up massive space inside the ship and bled power at every connection. The real breakthrough came in the late 1980s when Finnish engineers working on icebreakers for northern seas proposed a radical solution: move the electric motor directly into the rotating pod under the hull. If engineering stories like this grab you the way they grab me, subscribe to the channel right now so you don't miss the next episode. Hit that bell and every new video will show up for you immediately. The work was carried out by specialists from a shipbuilding company looking for a way to make vessels more maneuverable in ice. The first experiments looked risky. The engine had to be completely isolated from seawater and made to run for years without any access to it. In 1990, the first working units appeared, and just a few years later, the technology began being installed on actual icebreakers. It turned out that this design didn't just work, it worked better than any traditional setup. When it became clear that the azimuth thruster allowed a ship to move in practically any direction without turning the hull, the system was quickly adopted by cruise liner builders. This thruster can rotate 360 degrees, making conventional stern rudders and separate bow thrusters simply unnecessary. Maneuverability increases so much that a huge liner can pull up to a dock nearly sideways without tugboat assistance. Since then, this design has gradually changed the very concept of where a ship's heart should be. Not inside it, but right beneath it. I walk past hull sections that were still separate steel plates just hours ago, each one several inches thick and weighing several tons. These are already curved metal sheets, pre-rolled, so the future capsule has a smooth, streamlined shape with no abrupt transitions. No right angles here, no unnecessary joints. The form is dictated by water, not manufacturing convenience. Overhead cranes slowly lift these elements and bring them together like assembling an underwater projectile. Between the parts, they leave a narrow gap where the weld seam will go. During welding, sparks fly everywhere, and the metal glows orange. Workers move slowly, passing over every inch of the joint multiple times. No rushing, no wasted motion. First comes the inner seam, then the outer. And after that, the surface gets carefully ground down so there's not a single protrusion left to create extra drag in the water. When the hull finally closes up, it already looks like a smooth steel torpedo. Tight, solid, without a single flaw on the outside. After that, the inspection begins. Welds are scanned with ultrasound and X-rays searching for even the tiniest pores inside the metal. Any suspicious section gets cut out and re-welded, no compromises. Then they seal the capsule and pressurize it far beyond what it'll face underwater in actual conditions. If there's a weak spot anywhere, it'll show up immediately. Only after passing all tests is the hull declared ready to withstand years of service in cold seawater and constant ice impacts. Once the steel capsule is fully welded and tested, the moment arrives in the shop that the entire hull was essentially built for. They need to install the electric motor, the main power source for the future vessel. And this is where you realize just how massive everything is in marine engineering. Before installation, the motor sits on a special platform looking more like part of a power plant than ship machinery. Its diameter, nearly 10 feet, and its weight is such that regular lifting equipment isn't even considered an option. Only heavy overhead cranes work here, with every movement pre-calculated and coordinated. The rotor, the spinning part of the engine, gets lifted separately. It's a massive metal ring with copper conductors that weighs more than a fully loaded semi-truck. The crane starts moving so slowly it's almost invisible to the eye. The operator works on commands from several engineers stationed around the housing, constantly monitoring the component's position. There's no room for sudden movement and no room for error. Even a shift of a fraction of a millimeter can mean misalignment that'll show up during operation as severe vibrations. And vibrations at this power level aren't just an inconvenience, they're a disaster. When the rotor hangs over the open capsule, the most nerve-wracking phase begins. They literally lower it millimeter by millimeter, constantly measuring clearances with laser instruments. Inside the housing, bearings and support elements are already installed, and everything has to align to within thousandths of a millimeter. If the engine shaft is even slightly off from the geometric center of the capsule, a spinning imbalance will develop that the entire ship will feel. At operating speed, this imbalance turns into a constant hammering that can destroy bearings or damage the housing from the inside in a matter of weeks. After the rotor is seated, engineers won't allow the crane to be removed for a long time. A series of checks begins. They measure alignment, manually rotate the shaft several times, listen carefully to the sound of metal. The slightest unusual noise and the part gets lifted back up. Sometimes they raise the motor again and adjust its position, spending hours for just a few millimeters of correction. Everyone here understands. Once the capsule is sealed, there will never be access inside again, so perfect precision matters more than any installation speed. When the motor finally settles into place, the entire structure suddenly looks complete. An empty steel shell transforms into a real propulsion system. This is the moment you can consider the birth of a system that will later spin the propeller, turn a multi-thousand-ton vessel, and operate for years underwater, where no human will ever see it again. Modern units can pump out up to 22 megawatts of power. That's the equivalent of more than 30,000 horsepower. To put that in perspective, a single engine like this could supply electricity to a small town of 25,000 people. And this is a mechanism that operates completely underwater, hidden from view, impossible to service in the open ocean. It's designed with reliability margins years into the future because scheduled maintenance is only possible in dry dock. A fully assembled unit with engine and propeller can weigh over 320 tons. The propeller that attaches to the pod often exceeds 23 feet in diameter. Each blade on a propeller like that weighs as much as an adult African elephant. Yet this entire system has to run absolutely smooth. Any vibration at these power levels instantly transfers to the hull and gets felt by passengers on every deck. Once the engine is safely tucked inside its steel housing, the final stage begins, installing the propeller. If the pod itself is the muscle, then the propeller is the hands that push against the water and drive the ship forward. Each blade is manufactured from a special alloy of bronze, aluminum, and nickel. This metal needs to be strong enough not to bend under the pressure of thousands of tons of water, yet smooth enough not to create unnecessary turbulence. The blades arrive at the pod on special pallets, each wrapped in protective film like a piece of jewelry. Installation is carried out using hydraulic rams. The propeller is mounted onto the engine shaft protruding from the pod, and here precision is once again measured in thousandths of a millimeter. Any misalignment will cause the propeller to vibrate at operating speed, and that vibration will destroy the engine bearings within days. When the propeller finally locks into place, it's secured with a massive nut, tightened with several thousand Newton meters of torque. After that, a streamlined cap is installed on the hub to ensure the water flow past the propeller is perfectly smooth. The entire assembly is coated with special paint that marine organisms and barnacles won't stick to. Because even a few centimeters of buildup on the blades can reduce engine efficiency by 5 to 7%, translating to losses of hundreds of thousands of euros per year.
A tire built to hold a vehicle steady at 125 miles an hour is not poured, not stamped, not cast from a single block. It is assembled by hand, layer over layer, in roughly 15 minutes. And rubber accounts for only a quarter of what goes into it. The rest is petroleum, steel, carbon, and some 30 separate chemical compounds, bound into a formula Michelin has guarded for 130 years and never disclosed to anyone. A winter tire and a summer tire do not differ in tread pattern alone. They are two fundamentally different chemistries. A single tire for a mining haul truck stands taller than a grown man and costs 40,000 euros. The one riding on a Mars rover carries no air at all. And the deepest secret of all waits at the very end. Michelin was founded by two brothers, Edouard and André Michelin, in 1889, in the small French city of Clermont-Ferrand. In its earliest years, the company turned out ordinary rubber goods, gaskets, hoses, balls for hand pumps. Then, in 1891, everything changed. A cyclist named Charles Tarrant arrived asking for a repair on a tire glued solid to its rim. The job took 8 hours. Edouard Michelin decided it should never take that long again, and he invented the removable bicycle tire, the kind that could be swapped out in minutes, by hand, without tools. It was a breakthrough that reshaped an entire industry. The company never slowed after that. Today, Michelin stands as the largest tire manufacturer on Earth by revenue, having overtaken both Bridgestone and Goodyear. Its tires carry passenger cars, aircraft, mining haul trucks, tractors, and even the rovers of NASA. More than 130 years of unbroken work, and every single year the company produces something it did not know how to make the year before. It does not begin in France. It begins in Thailand, Malaysia, and Indonesia, the countries where the Para rubber tree grows, the tree from which natural rubber is drawn. Every morning before first light, workers move through the plantations and cut a thin spiral groove into the bark, deep enough to reach the vessels beneath, shallow enough to leave the wood unharmed. The tree responds. It begins to weep a white, milky sap called latex. Over the course of a night, a single tree releases about 1 fluid ounce, not much. But one plantation holds thousands of trees, and each can be cut again the very next day. The latex is gathered in cups, poured into vats, treated with acid, pressed into dense blocks weighing 77 pounds apiece, and shipped across the ocean to Europe. The journey from tree to factory takes several weeks. And here lies the paradox. All of it serves only a quarter of the finished tire. The other 3/4 comes from an entirely different raw material, made by an entirely different method. Synthetic rubber is made from petroleum, from the byproducts of its refining. Under the action of catalysts, chemical compounds line up into long molecular chains and become an elastic material, much like natural rubber. Much like it, but not identical. Natural rubber grips better under heavy load and sheds heat more efficiently at extreme temperatures. Synthetic rubber holds firm in the cold and resists aging under the assault of oxygen and ultraviolet light. Winter tires carry more synthetic. Without it, at 20 below zero, the rubber would stiffen like hard plastic. Summer tires carry more natural rubber. In every tire, the two are blended in precisely calculated proportions, set by climate, by load, by the range of speeds the tire must endure. A winter tire and a summer tire are not merely a different tread design. They are a fundamentally different chemistry within. And that formula is the central secret Michelin will not reveal to anyone, ever. At the factory, the rubber is loaded into an industrial mixer known as a Banbury. It is an enormous machine, tall as a 2-story house, in which 2 massive rotors knead the mixture under high pressure. Into it goes carbon black, the technical carbon that gives tires their black color and increases the strength of the rubber 4-fold over the untreated material. Without it, a tire would fall apart within a few thousand miles. Into it goes silica, for grip on wet roads and for lower rolling resistance, which feeds directly into fuel economy. Sulfur and chemical accelerators, which set off the process of vulcanization. Antioxidants that shield the rubber from breaking down. Processing oils, as many as 30 separate compounds in a single batch, each in a precisely measured quantity. The temperature inside climbs to 320 degrees Fahrenheit. What emerges is a hot, sticky, sharply pungent mass. It is not yet a tire, but it is already the material from which a tire must inevitably take shape. The rubber compound is rolled into sheets of the required thickness, cut into blanks, and fed to the building drum. Here comes the most unexpected truth of all. A tire is not cast whole and not stamped from a single piece. It is assembled by hand, layer over layer, like a precise, many-layered cake. The first layer is the airtight inner liner, which holds the air sealed within. Over it come the layers of cord, fabric of steel or aramid threads soaked through with rubber compound. The threads are laid at a strictly determined angle to the axis of rotation. It is the cord that holds the tire's shape under pressure. Without it, a tire would swell like a balloon at the very first inflation. The next layer is the belt. Steel threads crossed at roughly 20 degrees. The belt keeps the tire from expanding at speed and guards against punctures. And only after all of this comes the tread, the very pattern seen from the outside. Building a single tire by hand takes between 7 and 15 minutes. The assembled blank is sent into the mold, a massive steel structure weighing several tons, on whose inner surface the tread pattern, the size markings, and the direction of rotation are engraved to within hundredths of a millimeter. The mold closes. Through a membrane, hot steam is forced inside at a pressure of 220 pounds per square inch. The temperature reaches 340 degrees Fahrenheit. Vulcanization begins. The reaction discovered by accident by the American Charles Goodyear in 1839, when he dropped a mixture of rubber and sulfur onto a hot stove. The molecules of rubber stitch together through sulfur bridges, forming a single three-dimensional molecular network. The rubber turns from soft and tacky into something springy, tough, resistant to heat, to wear, and to ceaseless mechanical strain. The process takes between 10 and 15 minutes. After it, the tire can no longer be reworked or corrected. It is what it is, forever. After vulcanization, every tire, without exception, passes through a multi-stage quality control. First, a visual inspection under bright lamps. An operator hunts for surface flaws, blisters, cracks. Then an X-ray. The tire is scanned straight through. Inside, there must not be a single pocket of air, not a single shifted layer of cord, not a single fold in the liner. Then a test of uniformity. The tire is pressed with a force that imitates the real weight of a car and spun, while deviations in its shape are measured around the full circumference. The permitted deviation is fractions of a millimeter. And finally, balancing. The tire is spun up to the equivalent of 125 miles an hour, and any imbalance is measured to within grams. If even one parameter falls outside tolerance, the tire is scrapped. Not marked down, not sent for rework, scrapped. Because a tire that fails at 125 miles an hour is no longer a manufacturing defect. It is a catastrophe. Michelin builds tires for everything that moves, for bicycles and for the Airbus A380, for hatchbacks and for the Caterpillar 797 mining haul truck, which weighs 600 tons, a machine whose single tire stands taller than a grown man and costs 40,000 euros. For the cars of Formula One, where a tire lives 9 miles and costs as much as a used automobile. And for the rovers of NASA, where in place of a rubber air chamber, there is a metal mesh, because on Mars there is nothing to pump in. Michelin has developed the Uptis, a fully airless tire of reinforced polymers that cannot be punctured at all, in principle. It is already being tested on public roads in several countries. A company that began with a bicycle rim in 1891 is now seriously engineering tires for the transport of the next century, and it is doing so right now. On a shipyard floor that stretches farther than the eye can follow, a machine nearly 1/3 of a mile long takes shape, tall as a skyscraper, built to carry an entire small city sealed inside metal boxes. The modern container ship is one of the most complex and staggering objects heavy industry has ever produced. It does not merely move cargo between continents, it carries the weight of global trade itself. Electronics, clothing, spare parts, appliances, the machinery of everyday life, all of it can at some point cross the deck of a giant like this. Yet the most extraordinary part of the story begins long before the hull ever touches water. Building a container ship is not simply the welding of steel. It is a project measured in years, where shipbuilding, heavy metallurgy, digital modeling, immense logistics, power plants of colossal output, and a precision without which no floating city of thousands of separate parts could ever be assembled, all converge into a single effort. What follows is how these giants are built, why their assembly ranks among the hardest industrial tasks on Earth, and how flat sheets of steel are transformed into a true ocean titan. It all begins long before the first piece of steel is ever cut. The creation of a container ship starts with design, and it is here that the fate of the future vessel is sealed. Engineers and naval architects calculate cargo capacity, stability, speed, fuel consumption, the behavior of the hull in a heavy sea, the arrangement of the containers, the operation of the engine, the trade routes, and compliance with international rules of safety. A modern container ship is not simply a large vessel. It is a balanced system in which a single change ripples through dozens of other parameters. Even at the stage of digital design, the loads on the hull are modeled, along with the methods of lifting the blocks, the order of assembly, the distortions that welding will introduce, and the way the ship will one day operate at sea. This work can stretch across many months. In a very real sense, the ship is first built in its entirety inside a computer, and only then begun in steel. The approach reduces the risk of errors that, on a real shipyard, would cost millions of dollars. That is why modern shipbuilding begins not at the dock, but inside engineering software, where the future giant is assembled before it is ever physically born. After the design comes what can only be called the birth of the ship out of metal. Enormous sheets of shipbuilding steel arrive at the cutting bay, where automatic plasma and gas cutting systems turn them into the future elements of the hull, the decks, the bulkheads, and the structural members that bind it all together. A single sheet can run longer than a city bus, and any error in its geometry will echo through the entire project that follows. But the modern shipyard abandoned hull-by-hull construction long ago. Today, the giants are built on the block principle. From the cut pieces, workers first assemble panels, then sections, and finally large blocks that already represent substantial fragments of the future ship. Such blocks can weigh tens of tons, and at times, a great deal more. At this stage, much of the piping, the cabling, the internal passageways, and the equipment is often installed in advance. This is known as pre-outfitting, and it saves enormous time, because fitting out a single block on the ground is far simpler than carrying out the same work later, deep inside an already assembled hull. It was block assembly that made it possible to build today's ocean giants within any reasonable span of time. Rather than raising a ship piece by piece directly in the dock, the yard builds it like a colossal industrial construction set. Individual blocks are joined into even larger mega sections, which are then moved to the place of final assembly. But the larger the block, the harder the task of lifting and setting it in place. Here, the heavy infrastructure of the shipyard comes into play, the colossal cranes. Among them, the famous Goliaths, capable of raising hundreds of tons in a single lift. With their help, mega sections the size of an apartment building are moved with a precision that seems almost impossible to believe. The slightest tilt, an error in the points of grip, or a single distortion can turn an expensive operation into catastrophe. For that reason, long before the lift, engineers calculate how the structure will behave while in motion, and the assembly itself proceeds in a strictly defined sequence. Here the ship at last begins to take on its true scale, as separate parts gradually become a hull that surpasses in size most of the objects a person ever encounters on land. When the megasections arrive in the dry dock, the moment begins that can rightly be called the true birth of the container ship. It is here that the blocks are welded into a single monolithic hull. A dry dock is an immense protected basin that can be flooded and drained, allowing these giants to be built almost as though on solid ground. Inside the dock, the keel line is laid, the supports are set in place, and then, step by step, the hull takes form. The vast sections are fitted to one another, aligned, locked, and welded. At this stage, precision and the control of distortion become critical, because welding on such a scale always drives stress into the metal. In parallel, the ship continues to fill with its systems, as additional mains, engineering runs, the structures of the superstructure, and the internal compartments are installed. The container ship is, in effect, assembled like a steel organism, where every section has its appointed place and every error accumulates along the entire length of the hull. That is precisely why assembly in the dock is among the most demanding phases of all, for here the project, drawn from a digital model, is finally transformed into a real and living vessel. But the hull is only the shell. The true heart of a container ship is its power plant and its engineering systems. These giants are driven by enormous marine diesels that are, in their own right, marvels of heavy machinery. Yet the engine alone is not what matters most. It must be correctly tied to the propeller, the cooling system, the air intake, the exhaust, the fuel system, and the entire operating logic of the vessel. Engineers have long understood that a great many failures arise not from the engine itself, but from the poor integration of its supporting systems. A marine engine is, in essence, a giant air pump, one that demands a colossal volume of air and conditions tuned to perfection. If the ventilation of the engine room is poorly calculated, if the load of the propeller does not match the characteristics of the engine, if the logic of the cooling is broken, the entire system begins to wear itself down. The installation of the engine is therefore not the mere mounting of a heavy unit. It is the delicate engineering union of the ship's entire power network, and on it depends the vessel's survival in the open ocean. When the hull is at last watertight and able to float, one of the most spectacular moments of the whole construction arrives: the launch. For giants of this size, the dry dock method is most often used. The dock is simply allowed to fill with water, and a hull weighing many thousands of tons gradually lifts from its supports and begins to float. From the outside, it appears almost serene, but behind that apparent simplicity lies an enormous body of calculation. There must be precise understanding of how the distribution of loads will change, how the hull will behave at the instant it passes from resting on its blocks to being held by water, how the tugs will work, and how swiftly the vessel will reach a position of safety. After the launch, the container ship is still not ready for service. It is moved to the fitting out quay, where the work continues on the cable runs, the pipelines, the navigation equipment, the radars, the communication systems, the internal compartments, the insulation, the automation, and everything else that turns an empty steel shell into a real and working ship. It is at this stage that the future giant receives its brain. The final stage is the sea trials. This is the moment when the container ship first goes out to sea, not as an unfinished hull, but as a complete vessel, one that must prove that all its systems work together as a single whole. Tested are the maneuverability, the operation of the engine, the stability, the vibrations, the safety, the electronics, the navigation complexes, the communications, the power supply, the emergency modes, and a great many other parameters besides. Only after this can the ship be formally handed over to the customer. And it is here that one sees most clearly why the building of a container ship is reckoned among the most difficult assemblies in the world. This is no mere large ship. It is a floating industrial system, where thousands of tons of steel, miles of pipe and cable, an immense power plant, digital control systems, demands of safety, economy, endurance, and the capacity to withstand ocean storms for decades all must be brought together as one. A container ship must be more than gigantic. It must be reliable, because all its power is worth nothing without absolute soundness in the open sea. Seen whole, the birth of a container ship makes one thing clear. Here stands one of the summits of modern heavy industry. First, the vessel exists as a digital design. Then sheets of steel become panels. Panels become blocks. Blocks become megasections. And the megasections become a colossal hull that receives its engine, its systems, its electronics, and at last goes out to sea. All of it demands years, thousands of specialists, immense cranes, dry docks, and shipyards the size of separate industrial cities, together with an engineering precision without which such an object simply could not be built. And in this lies the true magic of shipbuilding. The container ship appears to be nothing more than a carrier of boxes. Yet in truth, it is one of the most complex machines ever made by human hands. It is born of metal, of calculation, and of discipline, only to become a part of the global economy. And every time one of these giants leaves port, behind it stand not only the ocean and the trade it serves, but the colossal industrial machine that proved capable of creating it.
Every year, millions of tons of wood waste are generated worldwide, and most of it could simply vanish into landfills. But this is where a remarkable story begins, transforming ordinary wood chips, shavings, and even old furniture into solid boards that become the foundation of our everyday comfort. This isn't just manufacturing, it's a second life for timber. Picture mountains of raw material as tall as a 5-story building disappearing into steel monster machines only to emerge in a completely new form. And right now, we're about to reveal all the secrets of this process, which combines scale, precision, and a touch of engineering wizardry. It all starts at a massive raw material yard, where the foundation for future boards arrives in a continuous stream. Contrary to popular belief, high-quality timber is almost never used in their production. On the contrary, the manufacturing philosophy is all about giving wood waste a second life. Mountains of raw material are brought here, reaching heights of dozens of meters. The foundation is industrial wood chips obtained from low-grade timber. A huge proportion comes from sawmill waste, slab wood, offcuts, and thin battens. Wood processing waste is also heavily used, such as shavings and sawdust generated at furniture factories. A separate and important category is reclaimed timber. Old wooden pallets, crates, and even used furniture are given a chance at a new life as part of chipboard after thorough cleaning. Every batch of raw material undergoes strict incoming quality control. The first stage of cleaning is removing metal inclusions. Powerful electromagnetic separators screen the flow of raw material, extracting nails, staples, and any other metal fragments. The material then passes through screening systems to remove sand, stones, and other debris.